Okay. Yeah.
We can watch you or Steve.
We are going to watch Steve. Here we go. And it is on gallery mode. And we're going to hit something called pin. And there's Steve.
Oh boy.
Steve, hi.
Yeah.
Howdy.
And there we go. So Steve, you got the stage here. You're about, what, 16 feet wide across the screen there? And your audio's good, so it's all your...
The diet just didn't work. All right, well, let me go ahead and share my screen with you, and you'll see the introduction, or there we go, hang on. Huh, now I can't see anything at all. That's interesting. Okay, wait a minute. I'm getting this. There we go. All that other stuff is not nearly as interesting. So I thought today I would take you on an exploration of what we've been learning with telescopes, and not starting with Galileo, even though I say that, and you'll understand why in just a minute, out to what we're seeing in the universe and a little bit of what we can expect in the next 4 or 5 years, and maybe more beyond. But anyway, I hope you'll find this interesting. I appreciate your listening to me this way. I really wanted to come, but even less did I want to expose anybody with what is not COVID-19. That I got a negative test on that, but I don't know what it is. It's just some kind of, it's close to a head cold than I can describe. So anyway, you may hear me having to cough occasionally, but overall, at least nobody's getting exposed except the screen here. So I am fine with taking questions. Just I'll just say feel free to interrupt me if you would like, or you can wait till the end, whichever way works best for you, and we'll go on from there. So the first telescope observations of the sky were made by Thomas Hariot. How many people knew that? Raise your hands. I can't see you, so it doesn't matter really. But actually he did beat Galileo by a few months, and we don't know much about him. We don't know much about him, and we know he did not publish his work, partly because he shunned publicity, and at the time he was also a close friend to a couple of people who were being held in the Tower of London, which is not a great place. You know, you can think of like Leavenworth or worse, whatever the island is in New York, where the prison come jail, whatever it is there is. In any case, he didn't publish his work. It has come down because some of the work was saved, but it didn't get widely portrayed. And of course, there is also Galileo, professor of mathematics, did work in astronomy, of course, you know that, and physics. And he heard about the Dutch telescope, deduced how to build one, and then started demonstrating it. As you all know, he eventually got in trouble with the church, and it only took the church 380 years plus to actually apologize. He published his work because even then, in 1610, it was publish or perish. He needed patronage, and some of that patronage he was hoping to get from the Duke of Medici. I don't think it actually worked out, but he did manage to keep going. He named what we call the Galilean satellites of Jupiter. He named them the Medicean stars. And this on the left is the closest thing we have to good replicas, at least, of Galileo's telescope. What is believed to be one of the original lenses, it's cracked in half, is held right down here. I hope you can see my pointer in the center of that support. And we have had in the past, the Riverside Telescope Makers Conference, people bring up their copies of his 2 or 3 telescopes that he built. And one night, nobody was standing on the telescope field near these telescopes, so I got to play with them and see what they would do. And boy, are they the hardest things in the universe to use. Fields of view are very narrow, and I'm just amazed actually that he did what he did with those telescopes, because we had a little bit of moon, so I could look at that. I could look for Jupiter's satellites, and it was very challenging just to get them pointed, and because of that narrow field of view. But it was fun doing it. So here is Thomas Hariot's first map of the moon. In fact, I think it is the first map of the moon. A couple of different styles that he used, and if you compare it with a more modern digital picture, looks pretty good. We can compare that, in fact, with Galileo, a much greater body of work, as you can see, but sometimes I find it hard to even figure out what he was looking at. And one example is here at the top on the left, also repeated middle right, or on the right side in the middle, I should say. I don't know why this is such a long, dark, weird shadowed kind of thing, except, well, maybe it is the moon, this half of the moon, but the shadows are way too strong. So and here again, I don't know what's going on. This big crater, nothing we can see like that. So his artistic efforts maybe were not quite as good as Hariot's, but at least he was studying the moon and could see that it would have been a sphere. Again, nothing huge there except for all the surface detail. Again, compare Hariot and Galileo, and their sketches of sunspots are reasonable. Actually, Galileo's look a bit better on the right than Hariot's on the left, but in any case, there were sunspots then. That was not to continue over the next 4 or 5 decades, actually, because we had what was called the Maunder minimum, with a great reduction in sunspots to once a decade or so, and reduction in auroras, and actually a mini ice age, it's sometimes called, in that time frame after the spots disappeared, perhaps telling us something about the sun's control of climate. Galileo, of course, did discover the Medicean stars. He illustrated here. First, on the very first night, he found 3. By the 3rd or 4th night, he realized that there were 4. And as you can see, he continuously made sketches and found that they obviously had to be going with being carried around by Jupiter. So Jupiter is now like a miniature solar system. And I think that helped crack the whole business with Earth being the center of the universe, even though Copernicus had said that wasn't the case a couple hundred years earlier. Galileo got a spacecraft named after him. Unfortunately, while we don't know for sure, we can be pretty sure that it did not look exactly like the one that was photographed here in the assembly facility at JPL, because its antenna did not unfurl properly, and despite lots and lots of efforts to do so. The good news, well, actually, just let me give you, before I tell you the rest of the story, going back to Galileo, we did get a lot of data. The good news was that they had planned to be able to, they put a tape recorder on it just in case they had to send things back slower or something like that. this antenna that was supposed to unfurl was a bit of greed on the part of planetary scientists, because there was a spare Voyager antenna, which is solid and would have done the job just fine. But they wanted to get, instead of 32,000 bits per second back from Jupiter, 40,000 bits per second sounded better. So they went with this larger antenna, which didn't end up unfurling, and ended up with a maximum of 150. That's no 1,000 after that, 150 bits per second, and at lower rates down to 8 bits per second, getting data back. Fortunately, it had the tape recorder. Unfortunately, even that had problems that prevented the 3 full disc, well, actually the 3 or 4 full disc pictures that were going to be combined into a color picture of the full disk of Jupiter, never got sent down, because the tape recorder started having problems. We had to avoid those areas as well. And so we do not have a full disk picture of Jupiter from Galileo. But we did get quite a bit of data from it. And here are some samples just to give you an idea. It's important to remember also that when we send spacecraft out, they do a lot more than take pretty pictures. And the pictures, of course, are used for the science, but there are also a lot of other measurements being made that tell us about those planets. Galileo observed Venus, and here's just some samples. He realized the phases meant that it was inside Earth's orbit and closer to the sun, and that was just another great step. And you can see some detail on this lower picture here by Chris Proctor, taken in the near ultraviolet, probably, just because you can see some of the detail of the cloud structures over Venus. That took a long time for us to see from the ground. Galileo observed Saturn and thought initially that there were 2 moons that, different from Jupiter, they were accompanying it around at the same distance. Later, he sketched this cup handles attachment, and you can imagine what had changed was the aspect ratio of what he was seeing, the orientation of the rings, and he never realized they were rings. Now, in this period, he also looked at stars in the sky, and he sketched this nebula in Orion. Some people have asserted that this nebula, which he sketched as stars, is Colander 69, which is illustrated here. I'll tell you, I have spent a couple of hours looking at that, turning it upside down, rotating things. Could I find any pictures that could match that? And I'm going to say not very well. So I don't know what to tell you. To me, that's still somewhat of a mystery, but maybe other people have really proved to themselves that it is Colander 69. In any case, he did find that the Milky Way had stars in it. Now, he was using a very simple mount for a telescope, which we're all familiar with, an Altaz mount. You see them being used for cameras, for instance, very convenient for looking around. Not so easy to use if Earth is rotating, because you have to move in 2 directions, both up, down, and sideways, to track something. And you might think, well, I know that equatorial mounts have been in use since the 1800s at least, but how early were they used? And there at Mount Wilson, of course, that you're going to be, and may have already, if you toured around, gotten to see the big mounts there for the big telescopes there. But what was done was just to say, let's turn it so that the rotation axis is parallel to Earth's rotation axis, and then we just tilt to get declination, and a clock can turn things. Great idea, right? Kind of an old one too. This is the earliest one I found, 1638, and you see there's the tilt of the axis as tilted here, and declination went up and down. This is limited just to the declination of the sun, plus or minus 23 degrees, and it projected an image of the sun on a sheet of paper so that it could be observed for sunspots or whatever else might be going on with one single motion once this is aligned with Earth's axis of rotation as well. So great idea, glad to see them in use, but didn't necessarily get applied to the telescopes. The other things that were going on right away was, of course, the Galilean refractor. He decided to use a negative lens here to reparallels the light to go into an eyeball following it. And that's part of the reason it has a very narrow field of view. The Keplerian refractor was first published in 1611. Just 2 years later, has a much wider field of view. I don't know why Galileo didn't adopt it, but in fact, by putting a positive lens there, it made a wider field of view. It was first used by Christopher Scheiner in 1617, and initially credited, I'm sorry to say, to somebody by the name of Skrill in 1645, because he claimed credit for it, but Kepler was the inventor. And eventually it came to be called the Keplerian refractor. Now, these types of telescopes suffer, as I think most of you know, from chromatic aberration. So the next step was, can we fix that? And spherical aberration. That's harder to fix in some ways. But yes, you can make the telescope really long. And here we are back at the telescope field in Big Bear, and you can see a modern day one, which sure looks hard to use. Here you can see a much older one back from the 1700s. That's 150 feet long. And just imagine if there was a breeze, much less a wind, to try and observe it. But the same basic thing is here. These are support lines, cables of some kind to keep the tube straight. The light gets through there trying to keep out some of the skylight around, and you even see, I'm going to go back for you, you even see a way to try and keep the telescope in that particular range for observing, and you see that right down here in this nice finished wood U and on the table. So there's an observer even looking. Looks like you might be even, I don't know what he's looking at, just for positioning, I think. So these things were built, I think the longest ever was 230 feet, and it's hard to imagine them being used, but used they were. And here is another example of that, with the objective lens here, the eyepiece down here, and a long cord holding the telescope together. And okay, I hope it works for you. I'm glad I didn't have to use it, but used it was. And the first recorded surface feature on Mars, we can all call it Syrtis Major. Here it is on Mars. Here it is in here. Was mapped by Christian Huygens. He also discovered Titan, Saturn's largest moon, in 1655. And if that weren't enough, he also discovered the ring of Saturn. And to make matters complete, he did what I consider one of the best actual written explanations, a scientific paper on how Saturn's rings will appear and disappear over time, and explained them by Saturn maintaining its orientation in one direction as it goes around the sun, and Earth sees that as well. And we sometimes see the rings stretching out all the way, and sometimes we lose them when we see them along the plane of their structure. We now know, and it's still one of those mind-boggling things, so I'm going to share it. The rings are much more than one ring, of course, you know that, but they also are not nearly quite as flat as they look. And so, but that took Hubble Space Telescope to really show that to us in some kind of detail. They're warped. Enter Giovanni Domenico Cassini, He became the director of the Paris Observatory, changed his name to Jean-Dominique Cassini, but it's one and the same person. Discovered Jupiter's great red spot. It also now appears, and I didn't find a picture to share with you, but he recorded a dark spot on Jupiter. Now, again, that's not too surprising because we know that the moons themselves of Jupiter, the Galilean satellites, cast shadows. But this one looked an awful lot like the collisions that Shoemaker-Levy 9 created and the scars on Jupiter that were there and then disappeared over a couple of months. And that apparently is something he may have seen and recorded, but could not interpret as we now can. He also discovered 4.5 moons of Saturn. In particular, he could not see Iapetus, which is down here on the lower right, on both sides of the planet, which was kind of strange. And he proposed that, well, maybe one hemisphere is actually dark. And sure enough, that's what Voyager showed us, and Cassini, the spacecraft, as well. He discovered this division, lower left here, in the ring of Saturn, and it's now called Cassini's division. Again, we have fine photographs of it from the Cassini spacecraft and elsewhere. And you can see it's not nearly as clean as it looks from the Earth. In 1989, Saturn occulted a 5th magnitude star, and as it passed through the rings, you could actually see some of the ringlets in the Cassini division blot out the star and have it return very quickly past as it was going through the rings. It was really something to see. The Cassini was an orbiter in the modern day here, and the Huygens was a probe that dropped onto the surface. There are arguments that could be made, and I imagine were made, though I wasn't around for them, that maybe it should have been the Huygens orbiter and the Cassini probe. But in any case, it ended up this way. And just here, some of those results, especially interesting, is what essentially could be a floodplain on Titan. And you'll notice that these are not jagged rocks. They look like they have been eroded by flowing with a liquid and bumping off all the sharp edges. And it's not just the one here, it's a lot of them are rounded. So there's something going on. I think one of the most fantastic pictures that Cassini, the orbiter, collected was this. That is a reflection off a pool of probably liquid methane and ethane at the North Pole of Titan, a reflection of sunlight coming both in through Titan's haze layers and back out through those haze layers. And the geometry was just perfect for a reflection and showing us that there really are liquid pools on this giant satellite. It's about 50% greater diameter than the moon. So we're talking about 3,000 miles or so. The other thing that Cassini allowed for us was some pictures that we can never see from Earth. And here is Saturn with in the direction of the sun. Here is the E-ring, a full view, and you can see where the Saturn's own ring system is thickest. The light is not getting through here, and thinner areas where it does get through. So a lot of what we do with spacecraft is go places where we cannot see what we can even see from Earth. Newton's contribution was what we call the Newtonian Telescope. And there you have one. For a few years, you could get these remakes, of course, that just for display, though they actually have a mirror in them. Mine has one, but it seems to have a bit of distortion that's not so pleasant to use. So I haven't used it very much, but it's fun to have and look around. This was the design he came up with, but apparently Nicolo Zucchi came up with this first in 1613. It's not, or sorry, 1616. It's not clear to me if he actually had in his design a secondary mirror as Newton added, or if he had a Herschelian design, and I'll show you one of those in a little while. But so a lot was going on in astronomy with telescopes once people got to thinking about it. And this 1616 is only what, 7 years after the refractor telescope was put to use on the sky. And here we come with Herschel. Quite a number of discoveries. He was most enjoyed using his 18-inch telescope, of which this is a good example. And it's an Altaz mount, rotates on the wheels down here, and altitude is adjustable up here. I think this might be just a lock or maybe a way of drawing it up for a little bit of correction. It's hard to know for sure without this, but without, you know, the instruction manual. But he also built a 48-inch telescope where the observer stood at the end here, and a head being small ignored the obscuration, and he had a direct reflection from this large mirror. That's why it's called Herschelian. He was using it a little off axis. Images wouldn't have been good, but he wasn't losing light by having two reflections. It's hard to remember, but we are very fortunate to have aluminized mirrors, aluminum coating on the mirror to make the mirror, which reflects on the order of 92, and with better coatings 95, and sometimes even more, a higher percentage of light reflected. This at best, when it was freshly polished, was somewhere around 45% of the light. And if you lose 45% twice, you're down at not much light getting through. So cutting that second reflection was a good idea. He made good use of it, discovering of his telescopes, discovering Georgium Sidus, we call it Uranus now, additional Saturn moons and another ring. And he looked at how the sun was actually moving in the Milky Way and got it pretty close to right. He said it's going in the general direction of Vega, the star, and did so. And of course, he's famous for mapping and cataloging the sky, not so much for his numeration scheme, which is inconvenient, but for the fact that he and his son later added 2,000, more than 2,000 objects, and the sun added another couple thousand. And those are all part of what we call the NGC, the New General Catalog, that was put together in the 1890s and later. So this is Georgium Sidus. Here is his projection of how the sun was moving, and here compared to a drawing of the Milky Way. And of course, now we have some idea that we are part of a barred spiral galaxy rather than a regular open spiral type of galaxy. To build a better refractor, Chester Moore Hall said, let's use two elements to do the light bending and make one of them negative to counteract the separation, this chromatic aberration it's called, and put everything back together. Well, you can't really do that with two lenses, but you can bring the two widest spread, well, any two colors of light together to the focus, and everything else is going to be better. And that's why later on the apochromatic lens was put together, which had three lenses and works better than two. And in any case, having an achromatic lens, as these are called, with two lenses together, worked much better, solving the problem of chromatic aberration. And it's much older than you might think. William Parsons, jumping ahead now, the third Earl of Ross, built the Leviathan of Parsonstown, a 72-inch telescope, and discovered, among other things, the Whirlpool Galaxy, well, Whirlpool Nebula, I should be calling it in that time. And Messier had put it on his list as number 51. So we call it M51, the Whirlpool, and found what could be done. Now that turns out to be something that nowadays we can do by a careful observer, can see the spiral structure with even a telescope as small as 10 inches. And somebody there might complain that, hey, wait a minute, Steve, you can see them even smaller, but I'll go with 10 inches. The era of big telescopes began, well, really began with the Leviathan, but it did not get a lot of use, and the weather in Ireland is just not really good for astronomy. And so the big telescopes kind of fell by the wayside until George Ellery Hales decided to build a 60-inch telescope, and taking advantage of the lighter glass mirrors with silver on glass coatings, they could build large telescopes. And by 1908, the 60-inch telescope was operating on Mount Wilson. His father offered him a birthday present of a 100-inch mirror made by a wine glass bottle maker in France, and he took it up on the offer, and the 100-inch Hooker telescope was built. I hope you get a chance to have a look at the back side of that mirror. You'll just find all kinds of bubbles all through it, through this piece of glass that's about a foot thick. And it's kind of amazing that it has worked as well as it was. The story, however, is, which you might hear or have heard already, so I won't spend a lot of time with it, was when they actually opened it up for first light, the images were terrible, just terrible. And you had a lot of disappointed people up there for that first light look. And they decided, well, we'll come back because the dome was open today. Maybe that's part of it. And sure enough, after it had a few hours to actually get down and acclimate to the ambient temperatures, sure enough, the 100-inch Hooker was a telescope of high quality. And it was very active and very important in astronomical history, well, on into the present. But by 1948, it was subsumed in size by the 200-inch at Palomar Mountain. And I'm going to emphasize now, because I may not get back to talking about Palomar, that it is really Palomar Mountain, not Mount Palomar. You can look it up. And it really helped that we could get to illuminization too. That telescope led the way to Edwin Hubble discovering essentially what we call the Hubble Law, that objects at greater distances move faster away from us. This in the lower right is the original Hubble chart of measurements of galaxy velocities, red shifts, and a few he did know had blue shifts, including this galaxy right here, that's M31 in Andromeda. But as a general rule, as far as he could tell distances, the further they got out, the faster they were going. And here is a much more modern view from his namesake, the Hubble Space Telescope, and Wide Field Camera 3 in this case, showing the changes in brightness of V1, this Cepheid variable star, which was one, I don't know if it was one of which, but there were several that he was observing. And we use those stars because they serve as standard candles. They're like a street light, all the same street lights going on down a street. And it's safe to assume that if they're getting fainter, they're further away. If you can, or if you think it's safe that they're all the same kind of street light. Well, you can prove that Cepheid variables are all the same, or at least with proper calibration are. And that was what he used. We now can extend this beyond the approximately 6 million parsecs distance, about 18 million light years that Hubble used, all the way out to distances of several billion light years. And it goes as pretty well a linear change. Well, things kind of went somewhat stagnant in some sense, and somebody might complain at me about using that word, but I will, with the growth of telescopes, until people started saying, well, could we put together telescopes out of segments and put them all together? And can we fly large telescopes in space? And the answer by 1992, the answer was a very definite yes. In fact, it was earlier than that. With Hubble, we were flying in 90, and segmented telescopes had been proven on the ground in Arizona by the 1980s. And so the era of space and giant telescopes began with where we are today. And so I'm going to take a look ahead now, and we'll see what we can see about that. John Herschel sketched M51 in 1828 and saw this. Lord Rosse, with the discovery of the Whirlpool Nebula in 1845, and this is just a modern black and white picture by Pedro Rey of M51, though in reality this is better than just a modern one, because if you look back at images taken with the 100-inch, with the 200-inch, most telescopes, you hardly see all this scattering of stars way outside. It's really just you see just generally the spiral structure. You see next to the Whirlpool, the companion galaxy, and not these things. This takes a little longer exposure to get them out, and that's very hard to do with photographic plates. Not impossible, but difficult. And so the things have progressed a long way to this Hubble image from HST. And again, you can certainly make out the stars scattered around here, but you can also see all those red areas, which are star forming regions, or at least nearby there will be star forming regions within them. And inside the areas, you've got hydrogen glowing in red. They're hydrogen 2 regions, ionized hydrogen. So we've really come a long way with making telescopes. We've learned that comets are weak. We've watched them actually fall apart. That wasn't too much of a surprise, because even as back as in the 1800s, Comet Biela was observed to split and then to not return, and we got a massive meteor shower on several occasions. At the time, it would have been close to Earth. And to add to that, but later we saw that besides Schwarzmann-Bachmann 3, we actually saw not the breakup, but we saw the results of a breakup of Comet Schumacher-Levy 9. And this is 2 of the spots that were created, the scars on Jupiter, this big one being the letter G spot, with the primary impact region right here, and the upflush. The outflow from that spread out and fell mostly in this crescent here. And it was a chance for us to see, as David Levy calls it, that the solar system is still under construction. But also there was another illustration somebody made right in that period and took the area of this that we see for the G spot and just had it land on the North Pole, and you end up seeing that this spray of material would have made it all the way to Earth's South Pole. So we found out that these things can be very damaging as well. Jupiter, they pretty much disappeared within 6 months to a year, but that would not necessarily be the case if Earth were struck by something like that. We've looked in much more detail at planets and moons. Here is again pictures from Cassini, or I'm sorry, this is Hubble Heritage, in fact, and you can see this is Titan, it is a place unto itself. You've already seen some of the geometry. It's been mapped partially by radar, either on the ground or by the radar, high resolution radar that Cassini was carrying. We have found Pluto and that it had satellites. One was discovered right away, Charon, not right away. It was actually 50 years after its discovery, but the two more were discovered, and then two more after that by Hubble. And we have since sent a spacecraft there. New Horizons is now 7 years past its visit to Pluto. We found that there are asteroids and, well, other oids. Still not quite sure what to do with calling these things. Many, especially in the planetary science community, do not like the idea of calling things dwarf planets. Ceres is one such dwarf planet. Pluto is one such dwarf planet. But as I say, there's a lot of debate. Yet we have something like Vesta, which is slightly odd shaped and with a lot going on, that is an asteroid, but not a dwarf planet. Pluto, I didn't bother showing you pictures, but the spacecraft showed that it has it. We knew it had an atmosphere. The atmosphere is doing all kinds of things to it, and it has surface features that you just would have thought would be on something larger than just a dwarf planet. Eris, with dysnomia here, has a satellite. Some of the other, but again, dwarf planets have satellites as well. There's one big one out there that is pretty clearly elliptical and still considered a dwarf planet. So why that's the case, I don't know either. So can't explain any of that, but we're still not being real consistent with our definitions, is what I'd say. And the universe has expanded in a sense with the actual discovery of exoplanets, planets orbiting other stars. We got pictures of this one orbiting Fomalhaut. So tonight, when you have a look out at the sky, wave to it when Fomalhaut becomes visible in the dark sky to the south. And it is actually still within a ring of material and could be adding material as it goes. This, of course, is a very long orbit around a beast type star on the main sequence. So typically we don't get to find them, but this one definitely seems to be moving and is real, though it looks like the speckle in the image mostly is just brighter. We've seen this kind of thing before, but never with this kind of detail. We're not so much seeing an expanding cloud of gas. We're seeing light expanding through a cloud of gas and dust over this period of 2 years, when there was a very, very bright flare of V838 Monocerotis, I guess it would be. And the illumination is making its way out to the extreme range of the field of view here. Be interesting again to see. You can notice that it was quite a bit brighter initially than here, because the stars that you see, and you can trace, they're all the same places, but they're getting brighter and brighter because a longer exposure was necessary as the cloud expanded. Not the cloud, I say it that way, but that's not correct. As the light echo expanded. Globular clusters. We knew that there were lots of large, giant stars in them. And sometimes you can see color pictures. I didn't grab one of those, but they will show them. But in fact, with Hubble Space Telescope, and in particular with Wide Field Planetary Camera 2, they picked up many dwarf stars as well, including white dwarfs, all through the core of M22 here. So yeah, that tells us more about these stars still, and these clusters. But it's nice to know that, that what we see is kind of what we expect. It's validation at times, and just proves also the quality here. Wide Field Planetary Camera 2 carried correcting actually mirrors. You'll hear them described as lenses, but they're actually correcting mirrors. The Hubble's, it's long forgotten by most people, but the main mirror had been incorrectly ground. It was ground perfectly wrong. But the good news was that the way WIFPIC was designed, it was possible to make corrector that would exactly compensate for that incorrection. And it only had to be the size of your thumbnail, about the size of a dime. Actually, that's not necessarily easy to do, but it was done successfully, as you can see. And that's what WIFPIC 2 carried up when it was replacing Wide Field Planetary Camera 1, which had to use the primary mirror as designed. WIFPIC 2 eventually came back to JPL, and I think it's probably moved on to the Smithsonian now, but I spent about half an hour counting micrometeoroid hits on the outer surface, because that was the only surface that was actually exposed to space. And I counted over 50 of them, little craters in the aluminum siding that protected and was the outer layer of the whole camera system. That was a fun thing to do, to be able to see that when it was on display at JPL. We've learned a lot about star and planetary birth. I give you fair warning, this is a wonderful picture, no question about it, but the colors aren't real at all, but it sure looks great. Mostly you would expect to see this as the same pink as the hydrogen here in M42, the Orion Nebula. This is a piece of the Eagle Nebula, but it shows the behavior of the dust clouds as well. And as they evaporate from stars not necessarily seen here, but stars are actually evaporating those dust clouds. We're in a system like this, you might, in M42, in the Orion Nebula, we see proplyds, protoplanetary disks, where we think, and have good reason to think, that there are planetary systems forming. And it's easy to imagine that they are forming in these very dense, dark dust clouds that it really requires infrared to see through, if at all. And in those dark clouds, stars are forming. Some of them can have protoplanetary disks that eventually converge and become planetary disks with planets in them. We can study star death now in much greater detail than ever before. On the quiet side, this is the cat's eye, NGC 6543, and the fine detail gives us an idea of what's going on. A lot of these things, the Ring Nebula, for instance, is not two offset spheres. It's actually a long tube. Think of a toilet paper core, the cardboard, and think of looking at it a little bit off the axis of it, and you would end up seeing, if it were transparent, two rings. That's how we have the Helix and the Ring Nebula, and even this one, though it has had a little more history to its eruptions as it slowly settles down into becoming a white dwarf inside at the core there. This, of course, is the Crab Nebula M1. It's really hard to pick out, but I think one of these two here is, in this general area, is actually the neutron star, the pulsar that is making the whole nebula glow. We see hydrogen gas, and we see the glow from electrons trapped in a magnetic field that are being spit out and captured by the pulsar in the center and being rotated around, and they generate light that gives this bluish color. It's called Charon. Oh, this is synchrotron radiation, and in the radio frequencies it would be cyclotron radiation. the violent explosion was observed by around the world, really, and visible for a couple of years to the unaided eye. At night and during the first month or two, it was visible in broad daylight, which is mind-boggling. But with Hubble, we can even see changes, and it's very, I don't even need to point it out, just watch what's happening in this area, and you get changes just all through this as something is going on, not necessarily understood very well, but over this 4.5 months or so, there is things to see that we could not see before with Hubble. The Sombrero Galaxy helps us better understand just the overall structure of tightly wound SA galaxies and the areas, the halos that they have around them at various distances, the clouds of gas and dust that are in them, and where they go. And here is NGC 1300, a great barred spiral, but also with bar structure and dust structure going through the bar, not something we see so often. Supermassive black holes are really a thing now, and Hubble paved the way with that too. We knew that there was this jet in M87 coming out. We could see it. We could see material actually over time moving outward. And in M84, Hubble produced this spectrum, which is kind of a duplicate. It had been done with Saturn rings years ago, but the equivalent is done now with the resolution of Hubble, doing it on the core of this galaxy. And you see huge blue shifts and red shifts of what has to be trapped material going towards us and away from us, from the direction, in the direction we are. And that's telling us that there is a supermassive black hole in the core of that galaxy. We can use the Hubble Space Telescope and others on the ground, big ones, and even some of the somewhat smaller ones, to look out and find that galaxy clusters are serving as big telescopes for us. They're actually creating and making visible more distant clusters of galaxies. They're easier to recognize because they have shapes like this. Or here's one, here's one, here's one, here's one, there's one down here, one up here. And there are many examples of other similar things where you can actually observe much more distant galaxies, because the light collecting power of a galaxy cluster is helping bring together, even if distorting. They really need to get some correctors on these lenses, the galaxies that we see back there, but the studies can be done spectroscopically. And in fact, if you look out and are able to, and it's not that hard, identify several of these images of the same galaxy, and you watch for supernovas in them, you could see one kick off. And I'm not saying these are the case, but if one kicks off here, that's the same one, and it turns out it appears here next and next and next, you then can do an actual trigonometric measurement of the distance of these galaxies using the light travel time and what would have to be, based on the lensing, the distortion and the extra distance the light traveled, because it's not going the same distance from here to us as from here to us. It had to travel across. Then it was bent a different amount. And so we can actually get a trigonometric distance and compare that to the Hubble distance and find out that, yeah, Hubble got it right. We also have, and something I've completely left out, is radio telescopes now. And radio telescopes add things that we simply cannot view. This is the cluster of galaxies in Perseus. It turns out we know from actually looking at the bending of light in the clusters in this general area, that there is dark matter on the basis of seeing, and you can see if I keep going here, you'll see a few of these. They're a little hard to see, but they're indicators of lensing. They're indicators of dark matter in the galaxy, and the gas in this cluster of galaxies in the foreground is impinging on with a lead set of galaxies and gas into another galaxy cluster over here. And we're seeing that collision going on in real time, though real time might have been 50 or 100 million years ago. But we're seeing the effects, first of all, of the gas being compressed by its collision with other gas in the other cluster, but also that the mass of those two clusters that are colliding is actually, some of it is dark matter. That's what's indicated by the blue, and it doesn't get compressed the way gas does. So we don't know what this dark matter material is at all. And that's one of the things that is a major mystery. And I'm willing to say that there's a Nobel Prize in there for somebody when they figure it out finally. So this is Hubble's deep field. It was the first one taken. I still love looking at it because in its complexity, it's simple. If you go around looking, I've done it. I was only able to find 3.5 stars in it because they're the ones that have the diffraction pattern, the cross pattern that you see like here, here. I haven't looked to remind myself where the others are. That might be one up there, but they're about 3.5 here. And all the rest of these are galaxies. And so you wonder why we need big telescopes on the ground. Why are we building all the ones that I'm about to talk about? It's because if we want to explore the behavior of all these little bits and pieces, which are actually small galaxies that have not in their time actually condensed yet into or been cannibalized by larger nearby galaxies, but they're all small ones. And we'd like to understand how they behave when stars are first getting formed, when there aren't as many other elements. And for astronomers, any other elements besides hydrogen and helium are just called metals. All those stars are mostly pure hydrogen and helium, and we'd like to understand that. One way to do that is to be able to look back and study the chemical concentrations of those elements. And another way is to look more directly at them. So we build these giant systems. This is the Very Large Telescope in Chile, and it uses 8.2 meter diameter mirrors. The Palomar 200-inch is a 5 meter telescope. And of course, the 100-inch is a 2.5 meters. So there's your scale for you. These can be combined together as one telescope interferometrically. And in fact, they can add on even these smaller ones, and tied together, they can get very, very high resolution. These can also be used as single 8.2 meter telescopes if desired. And there is a lot of science to be done with the high resolution and or the high light gathering power that's possible. You will, if you haven't gone on the tour yet, you will probably get to see the Georgia interferometry system that has 6 small telescopes. I think they're 40-inch mirrors in a pattern that they actually had to helicopter the telescopes up to be installed in each of their domes, just to keep the domes smaller up there on Mount Wilson. So just to begin my wrap up, I've already talked a little bit about planetary spacecraft and images and their science. The next generation of space telescopes are being launched, and extremely large telescopes are on the way. And I want to go a little bit off into the rest of the spectrum now. So James Webb is one of those things that's both one of those next generations of space telescopes and used in the infrared. Its near IR camera, a near infrared camera, actually extends out to the green part of the spectrum. But Webb was designed to be looking at as far as we can see into the universe. So it's about 6 meters across, as you probably all know. It all had to be folded up and fit into a rocket to carry it up. And it has returned some of its first pictures. And that was exciting too. I want to start though with just what they did with having 18 mirrors. When they finally got them all unfolded, this is the upper left picture is the one that with the segment identifications, and that's not really important, but you can see that there were, like, if you count them, it actually looks like there might be only 18 or 14 or I can't remember, 15 or 16, something like that pictures. It turns out some of them are close together. Each one of those segments was not well aligned. And I was a little worried because I said, boy, there's a lot of distortion there too. Well, the good news is, of course, that they brought them all together, it looked just like this. And they say, look, this is even better than we were expecting. What nobody mentioned in the course of saying, isn't this a great picture, which it is, was what's all this in the background? And all this in the background are those distant galaxies that they're hoping to look for with J-West. And so this was just a hint of what was to coming. I also point out to you here that there are a couple that the 6-pointed diffraction spikes actually are partially from the 3 supports here that are hard to see in the picture, and also the edges of each of the segments that was used to put one of these together. Each one of these segments is, by the way, about the size of the 60-inch mirror that is at Mount Wilson. They've just been cut down to that shape. And so that combination of all those optical effects gives you something like this with the test star. It gives you like this with Triton, but whoever heard of getting diffraction spikes off of a star, off of a planet's largest moon? And but you do. And this is Neptune, and Triton. And so you see the 6. You also see a pair of spikes here. I'll point out those 2 spikes here as well. And I'll tell you, I'm still waiting for a good explanation for why there is actually a cross pair of spikes. You can't see them; they're lost in the main diffraction spikes here. But in fact, in other star exposures, if you look carefully with not as bright objects, you can see a full cross, 2 forearms cross, and then the standard 6 that you'd expect. And I'm still puzzling over that. This is the James Webb first deep field. And now you're all experts, and you can see all these curved galaxies. Look at the distortion in this one, or these over here, and this one, and these, and here, and here, and here, just there, all over. Close galaxy clusters are lensing distant galaxies. And what people have done, which is rather amusing, is they've taken all the data that they can. This is people, astronomers. And before they even had the full calibration, they were starting to say, well, this looks like a galaxy. And I will take a step back in a second and explain the language I'm using. But the redshift has a Z of 17 or 20, were 2 of the original initial claims. Z is a way of describing the redshift, not in kilometers per second, but just in a measure of what the original wavelength is like and what it must be because it's redshifted. So a redshift of Z of 17 means you subtract 1 from that. That's just part of the arithmetic. And it's a shift of 16 times what the wavelength would be in a laboratory. And so that's a lot, because the most we've measured is about 8, maybe 10 from the ground. And so everybody is celebrating, and then they had to start retracting all this stuff because they didn't realize that there was not a good calibration on all the images that they could play with. And so it still looks like they're high redshift, but I think we're going to have to wait for more than just the quick reports to abstract to post bulletin board posts to do that. I actually do mention, will bring to your attention again some of these fainter stars. In fact, this one's a good one here. Here you can see just a lot of diffraction spikes in a lot of different directions. And there is a cross here, there is a cross here, there's another set of 6. I have not figured out all the diffraction spikes, and it's just really frustrating to me. But maybe somebody can. I'm sure they can. Coming up 2 years from now, the predecessor for this huge telescope is one that's in New Mexico and has been doing more than a dozen different surveys of the northern sky by just letting essentially the sky go by as it sweeps it with its CCD. And the wide angle surveys like that, surpassing what the Palomar Observatory Sky Survey did with two of them did with the 48-inch Schmidt camera there, it has really been valuable. So if a 2.5 meter telescope is good for that, why don't we build an 8.5 meter telescope to do the same thing with even better, more modern technology, not from the 90s or early 2000s, but from the 2020s. And so this is anticipated to be in operation around 2024. It was formerly known as the Large Sky Survey Telescope, LSST, or large, actually it was Large Synoptic Survey Telescope, and able to actually do the whole sky in 3.5 days or so. They changed the name of it to the Vera C. Rubin Observatory, with the Simony Survey Telescope performing the legacy survey of space and time. Great name, but to me, it's one of those examples that there are certain physical laws that never fail, and this is one of them. An acronym is always preserved, just as energy is never lost or gained. An acronym is always preserved, and so we have the Large Synoptic Survey Telescope, when it was first proposed, becoming the legacy survey of space and time, coming up in less than 2 years now. Coming up also is the Nancy G. Roman Space Telescope, formerly known as the Wide Field Infrared Space Telescope, launching in 2027. Nancy Roman was an astronomer and a associate administrator at NASA, and it is actually the same size. It was a donation from the Department of Defense of one of two 2.4 meter mirrors. That's the same size as Hubble, which could be used for looking up instead of looking down. I'll leave the looking down part to your imaginations, but yes, that's what it was. And just report to you that in this case, the difference, why repeat this? Because the Roman Space Telescope is going to have a much larger field of view than Hubble does. And again, that's to do deep surveys and be able to look for closer to the actual structure of the universe, something that is also done in other wavelengths, in the radio in particular, and by other means, but is something that can be done optically as well, and that's what this telescope is going to be doing. So we've got a lot more exciting science on the way from space. Now, also, we can do science with balloons, we can do it with rockets, and we do it with satellites. And just for the record here, we're starting in the radio continuum. That's just the wavelength that we get. We see atomic hydrogen, looks different. Radio continuum at a different frequency looks different. Molecular hydrogen looks different. We're seeing all kinds of things, no matter what range of the spectrum we look at. We have gamma ray and X-ray down at the bottom. Optical, that's where you are right here. Near infrared, mid infrared, far infrared. We got all kinds of science to do with all those. And one of the most exciting things that has come up in the past few years is actually seeing a black hole, or the shadow of a black hole. This is interferometry, again, a collection of about a dozen radio telescopes that spanned Western Europe to Hawaii and from Boston to the South Pole, that made measurements that could be combined to show the central core of M87, which has that long jet coming out I pointed out earlier. And this is what that core looks like. It's not nearly as active as the Milky Ways, which they also measured and only released about 3 years later, because it was so hard to figure out what was going on and get it all to work together. But from this, you can see where the gas is coming from that falls in. The spiral network there is indicative of some of the magnetic fields that are there. And we are actually seeing as close as you can probably get to seeing a black hole. You can't see them because light can't escape from the inside, but you can see light that it might be coming from the far side from gas clouds on it, or a disk of gas around it. It blocks it. So that's why it's being called the shadow of the core of the galaxy. And this is just one of those really cool things now that we get to see for the first time. Things that we don't get to see, like ever, include neutrinos, but we can see their effects. And neutrino astronomy really started with the solar neutrino problem when a group of when somebody put a tank of cleaning fluid down in the bottom of a mine to count neutrino interactions with the chlorine there, and wasn't seeing enough of them. It was only seeing about 1/3. And it took a while, and then there was a Nobel Prize, because at the time it wasn't clear, well, do we not understand what's going on in stars properly? Or is the sun misbehaving? Or are neutrinos not behaving the way we thought? And it turned out to be the latter. Neutrinos weren't behaving the way we thought. Turns out they can transmute themselves. And so that was a big deal, learning that. So we do understand how stars work, at least have a pretty good understanding of a regular main sequence star. And then supernova 1987A made its appearance. Well, at the time, I'll say first discovered visually by Oscar Duhalde, and then later a New Zealander in New Zealand who tried to actually notify people. Oscar didn't say anything about it, and it only came up later that he was maybe the first one. The New Zealander, unfortunately, had a bad time with the telegraph getting the message to the Central Bureau. And so eventually it all got sorted out about who the discovery was made. But what was more important, this was the first naked eye supernova since 1604, since Kepler's time. And the folks who run Kamiokande and another, I forget what IMB stands for, but it's a neutrino telescope. It's a vat of water that shows, now I can say it, Cherenkov radiation from collisions with neutrinos and the atoms in the water. And they could actually see the explosion from the neutrinos escaping from the supernova about 6 hours early compared to the visual discovery of the supernova. So that's how you get to doing neutrino astronomy. Now we're doing it even better with the ice cube. There's a 1 kilometer cube of ice in, so that's 0.6 of a mile on a side cube in Antarctica that is filled with this kind of sensor that looks in all directions for ice. And it's looking for, again, that blue Cherenkov radiation. And they have actually identified neutrinos coming from a blazar 4 billion light years away. And that is very, very impressive science. And in fact, now the neutrino observatories are, I think, tagged into the notification system. So astronomers, if there's a blast of neutrinos that is detected, they'll know to start looking for a supernova. And in fact, there are other things that they can look for as well. I'll get to that in a minute. I want to mention also cosmic ray astronomy. It's neither of well, neutrinos and cosmic rays are not electromagnetic spectrum. They're not radio to ultraviolet and gamma ray and X-ray astronomy. They are a whole different case, and so are cosmic rays. You can actually use these large telescopes just as light, and they're just light buckets, looking for the flash of a cosmic ray, typically a hydrogen, but it could be something much heavier element-wise, hitting atoms in the atmosphere, creating that light, and secondaries creating more light that eventually you can see some of that picked up by the light buckets and measure them. You can also see it as Cherenkov radiation coming down through and into these particle tracking devices, of which there are some that can be of various types. Here's one that's high altitude water Cherenkov observatory there. So we're learning about how gamma rays and cosmic rays create, not just create, but what those gamma rays and cosmic rays can tell us about the outer universe. And finally, gravitational wave astronomy has reached a point where it too is signed into the notification networks, so that if there is a discovery of a gravitational wave, they can now, not with just the two here, there's a third gravitational wave telescope in Italy that is contributing, and they can narrow down the area on the sky to about one degree or so, and maybe even better. With that, there are additional gravitational wave telescopes on the way in the next 2 or 3 years, and they will be able to even better pinpoint where these occur. We have now seen black hole collisions. We've seen neutron star collisions. We've seen neutron star and black hole collisions. It's just fascinating science at the most extreme sort of places. And I don't know if we'll ever see a multi-million solar mass black hole collide with anything, but maybe sometime. But this is marvelous science, so, and worthy of a Nobel Prize. It only took 3 years for them to vote for that. So it's wonderful science. So I hope you have an idea now of where we've been and where we're going. And I just encourage you to keep on looking. And there are ways that you can participate this by participating in Zooniverse, ZOONIVERSE, and contribute if you want to. In any case, clear skies.
All right, thank you. Any questions for Mr. Edberg? I think you covered the whole universe, Steve.
Is anybody awake? That's what I really want to know.
They're all awake.
Okay.
They need to take a little break here.
All right.
We're going to take about a 10-minute break or 15-minute break, and then we'll come back on. We got 2 more speakers, and then we're going into the 60-inch dome. Okay.
All right. Clear skies tonight, everybody.
Thanks, Steve. Take care.
Okay. Bye.
He does, doesn't he? Yeah.
All right, Scott.
Thank you.
Yeah,
See you Sunday.
yeah. Give me a call when you give me a little heads up.
I sure will. Take
All
care.
right, take care.
Bye-bye.
Good viewing.
I was just telling Diana, when we see 100 years ago,
Yeah.
what they were doing here, okay, and now you're seeing this. It's not just that; it makes you feel very privileged to
Mhm.
be able to even witness the science that's cutting edge. Because back then there was no internet or whatever.
No, that's right.
when
This was
Hubble-
all closed
when
off,
he
right?
discovered all that, it was all iron wall. And
Yeah, yeah.
also the
Harlow
comprehend-
Shapley, when he
Yeah.
he knew,
Yeah.
he had figured out that that the sun was not in the center of the Milky Way.
Yeah.
There was no one for him to tell.
Yeah.
He found a lady that was working over at the
Yes.
monastery,
Yes.
and she was the first to know.
Yes.
Okay.
And even if he tells, how does he explain and impart how he knows? Like all the science that's required.
I'm sure they believed him,
They're like,
just
"Oh, yeah,
because of
yeah,
the
okay,
stature
no."
who he was.
If you said stuff that didn't jive with the church,
Yes.
you could
Yeah.
be executed.
Oh man,
Well,
I mean, I only got 10% of but
Yeah,
I could I know enough to see, like, wow, to appreciate the level of science that's going on.
Mhm.
And you don't create these structures and all these things, just because you don't know what you're doing, right? Like,
Right.
Crazy.
it's really major.
What he was hitting on. is
very smart people.
Part of my lecture too,
Yeah,
about the 19th century astronomers were sketchers. They didn't have cameras.
right.
So they worked with a consortium of people and they would share their ideas.
You're doing
Now,
this
you have PowerPoint or something?
Bjorn's gonna do my images and I'm gonna talk about each one. I have my whole thing.
Okay.
referenced.
So Bjorn is, he's got a laptop or something
Yeah,
else
he's
here?
got his laptop.
All right, so he's
Bjorn.
going to need to know, thanks, Cameron.
Bjorn, flip it up.
So I actually have very I just have 10 minutes or 7 minutes. I just don't want to plug directly into the thing. That's the easiest thing to do. Oh, they do. Oh, they can't. Yeah, we're still on. Probably see it already. Whatever. amazing.
Wait, what is this?
Yeah, you know what? Yeah, the one with it doesn't, I don't get the Wi-Fi signal unless I'm up there. I don't know, I have the same problem. I need to download one more. And it's just search. And I took the computer. Once you send me the whole thing, I go off.
We gotta go right there. I wrote that whole box.
I was gonna send you maybe. So then you're gonna have to. It's just 5 minutes, right? Or 6 seconds. They're all numbered. So
He said.
I have a 4K file, I have a 1K. But putting on screen. So it's like 4 days. Oh, wow. Start all over. It's not just a while. Oh, because through the Wi-Fi.
Don't you want to get one?
It's okay. Should take this.
That's all.
All right, so it's all you. We could also take it. So I would start with images. All right, so my email address is. Okay, I don't have any. Yeah, let's go with the other file. This program is switching on. This program is switching on. It's like you put in the car. Mine's pretty.
The box is in the car. That's why I wanted to come with.
Go faster than
Okay, well, this is my mom.
So what time do you turn on the cloud dispersal machine?
Sunset. After the energy gets out of the air.
And actually, it looks pretty June blooms hanging around this year.
Didn't happen in June, it's happening now.
Exactly now. So we lived in Orion Nebulas. Well, on top of Rolling Hills,
Yeah.
1980 to 2007. And after my boss said he couldn't afford me anymore, we left. Retired person and a half. Come back out for this. We've been at it for a week, and all in June blue. I'm like,
If we didn't have it in June,
that's weird.
yeah. Running to the end June, one in September.
I didn't change.
It's, we've got some strange, very strange patterns.
In Arizona, we're really just on the two, so.
Yeah.
Back on monsoon season. It's still going on, although officially in.
I know, we see it over there in Riverside County, we say, yeah, they're really good showing.
Yeah, we're getting some, and we had, Scott had a big start party. And two of them, what could have been really good nights, we had a
storm, hail, lightning, power outages. So all those people who didn't live in Arizona got to experience real awesome. But this has been a crazy year for the middle of middle of June to the week of the start. 5 different miles. Oh my gosh. That's unusual. Now, start burning. But this is a wonderful place.
It is good.
We were here, we visited Char shortly after opening.
Two, four-ish, five-ish.
Okay.
It was in several stages. of opening.
Yeah. So we got to they got us through the Friends of River. Okay. And then I've been up here in 1983 with my older brother. And that's why I had to go there. So my autobiography. Let's see. 70s, 80s. There we go. Oh, okay. So that is my oldest brother. This is my brother who started the astronomy 6 years ago. Wearing the same hat I had when so we were great.
So yes, and you don't throw away.
I don't throw I don't throw anything away. That's right.
It's getting dark in here though.
Yeah.
I can turn more lights on.
Let's turn on some more lights.
We don't want any light pollution.
We're priming ourselves for 60.
Okay.
Where are the lights, Chris?
This one, that's the number.
I just figured something out. I can't send you to people. Oh. There's something about songs and returns and things, but everybody's like small blocks everywhere. I'm sure it's probably interesting. It's all spring good. Or restaurant. Actually, the right side of the board, you have to walk into the front room. And then
There's two, there's a guest and there's.
Yes. It's still. Oh, good. But I want to make sure that the sound comes up. Okay, we have some time, right? Yeah.
Is that a mini?
It's the mini.
Nice. Is that the new one with the Apple chip in it?
Yes.
Nice.
This is stuff together, right?
Sky people all there. So it's the one.
Which one?
No, can't read the whole title. So Sky People 4K. I can't read the whole title. Oh, I see. Can you make it so that it's a greater or whatever it is? You know, the one with the icon above that folder.
The one on this.
Click that one. That's columns. Oh, there you go. That is it too. So yeah, that's the one. So the top one with that's it. Yeah. That's the one.
Okay.
Yeah. So you probably just play it from the drawing. Oh, you need to disconnect.
Yeah, I do.
Yeah, so that's the one.
And then you got mine already. Somewhere.
Yeah, I will transfer this. Start to your desktop.
Yeah, it's a lot of stuff. Sky People, some of it is, yeah, the top one.
Stop talking, I'm bored. Stop talking, I'm bored. Just keep doing that until the rest of the meeting.
Looks like it's loading. Yeah, it makes so much more sense that you play that from your computer.
Yeah, most of the videos I play are about 300 to 400 megabytes.
Oh, really?
That's a big one. Yeah,
That's 4K.
it is. I mean, all the NASA stuff and everything shows about that.
Well, it should play it, right?
Oh, it'll play it. It'll play it.
Do you want to check and make sure mine went in?
All right.
Mine's easy.
Yours is in already.
How did lived without retransfer, before retransfer. How did we do that? I don't even remember.
There was others.
Really?
Yeah.
I never remember anything.
Yeah, really big files is one. It was kind of 5 or 6 competing.
All I ever remember was 9 gig cinder block.
Yeah, right.
And then you would drive around town with those. That's all I remember. Why is that all?
Now where?
From the wormhole. That came out of that black hole.
Okay.
So we're done. We're done.
So when I speak, I just speak. I don't have to stand in front of the mic, right? Or should I?
Yeah, you should.
Yeah, you need to talk into these mics.
Yeah, because if you don't, it's so echoey, it's really hard to do.
Oh, Mike did it. It sounded pretty good. Easy.
Yeah, no one in our streamcast is going to hear you.
Yeah, no, I'll do that.
Yeah. Or it's going to be very faint.
Right. I hope I didn't complicate things too much.
Yeah, that's normal stuff. Let's see if this looks better somehow. I do need another light. Here we go. Okay. For those of you that are still watching the screen, we are just taking a break here at Mount Wilson, and we're about to get started with another talk. We have Chris Burns from Carnegie Observatories coming up next, and then after him will be John Schwartz. And so, and then we're heading into the 6-inch, and I'll try to, I don't know if we can or not, but we'll try. Okay. We have
Quorum?
a quorum.
There's a couple of slides, but one's 10.
Yeah, let them know.
Okay, I'll just bring my talk up. So let's see. Okay, that's full screen. No, okay. Stop one. There.
It's Hubble trouble. Yes,
So I'm sharing this through Zoom. That's the right thing to do?
That's what we're doing. Yeah.
Okay, can tell by the
We
green.
are live. Thank you for your patience as we transferred to a new talk here. We just had to have a little break there. We are still live from the Mount Wilson Museum, on the historic and hallowed ground here that is Mount Wilson Observatory Complex. With us is Chris Burns. Chris is from Carnegie Institute, the Carnegie Observatories, and his specialty is supernova. But he is well known here on the mountain, well respected in the scientific community. And, I hear, as I told him earlier, only good things about Chris Burns. So I'm really proud to have him here. It's been nice to get to know him a little bit. And so I'll turn it over to you, Chris. Thanks.
All right, thanks. Yeah, so I work at the Carnegie Observatories. So I am paid to be an astronomer, but I get to volunteer up here, which is awesome. And glad you guys can make it. The thing I've been working on most for the past, gosh, I want to say 10 years, but probably more like almost 15, is this Hubble Constant. And I'm going to give you some history about it. I'm going to give you sort of the modern take on if there's actually what we call this crisis in cosmology, and the latest results, which are actually only a few days old. So no cell phones, no pictures, no social media, please. It'll be preliminary stuff. Okay, I like putting this cartoon up because it kind of summarizes how I feel a lot of the time. We've been at this for a very long time. And you can almost argue that cosmology is one of the oldest sciences, if not the oldest science. We've been trying to figure out where do we come from, where is this all came from for a very long time. And we've been telling ourselves lots of stories about how it happens. And some of those stories had no evidence to back them up. And the stories we tell ourselves now have little more evidence to back them up, but there's still a lot we don't know. And primarily, the reason that we don't know a lot of these things is because distance is really, really hard. This is one of my favorite things to look at. It's not up tonight, it's a little bit too late in the season, but there are two objects. I'm going to use my mouse so that people on Zoom can, oh, is it not going to let me point with the mouse? Goodness, let me see if there's a way to do that. Someone with better eyes can see that.
Black mouse and black background.
Oh, is that what it is?
Put it in the window, try to get up to your image of the Zoom that they're seeing. You might see it up in that window space.
Okay, there's the mouse.
There you go.
All right, and now if I play, it doesn't seem to be there. Oh, well, we can, I will pantomime. But there are two stars kind of in the middle there. They look more or less one like the other, but they're not the same. What is that now saying? The transparent from meeting may be saved. Okay. All right, I've lost my mouse control clearly. What if I do this? Oh, no, that's not doing it either.
You need a laser pointer?
Oh, that'd be great. Oh, there we go. Okay, so the one on the right is a star in our galaxy, 25,000 light years away. The one on the left is a quasar, 2 billion light years away. This is probably one of the most distant objects you can see with the human eye with the telescope. This is why I often like to show it to folks like you who would really appreciate seeing something like that. It's called 3C273. And here's the problem in a nutshell. How do I know one is a quasar and the other one is a star? Just by looking at it, it's not obvious. So we have to figure out ways to do distances. So here we have night sky. And there's this other thing, faint fuzzy, which I don't know if you can see it in this screen. It might be a bit too bright. Just off the constellation of Andromeda, you can probably guess where this is going. But that was a smudge, and those smudges have been known for a very long time. Even before telescopes, if you know where to look on a really dark night, you can see the Andromeda Galaxy with the naked eye. And there was a big debate, what is this thing? And we don't know unless we know how far away it is. And it really took two major breakthroughs in astronomy in order to figure this out. One of those breakthroughs was methodology, and that was pioneered by Henrietta Leavitt. She discovered that there are these variable stars called Cepheid variables, and that you can figure out how bright they really should be, or at least relatively speaking, how bright one Cepheid is relative to another. And all you have to do is measure the period of oscillation and you can get the result. So that was her contribution. And then on the other side, we've got instrumentation. And George Hale is responsible for creating the largest telescopes at the time. And so you've got, on one hand, a new technique that you can use to figure things out. And on the other hand, you've got the instruments that may be able to help you do that. And you're going to need a bigger light bucket. So on the left is a time lapse of the 100-inch, which I find kind of fun to look at. Also get this effect that you guys saw today when we were up there, and it looks like the telescope is spinning, but really it's actually the dome that's spinning. And on the right is the cage we were talking about with Newtonian focus that hopefully will be coming back to us very soon, but that would have been the cage that was at the top of the 100-inch when Edwin Hubble took his very famous plate of Andromeda. And here is a up-to-date modern version. I think this is probably from Palomar. And if you rotate it just right, then that's where that famous VAR plate came from. And we saw that in the dome of the 100-inch. And I remember somebody had asked at the time, what were all those ends for? Yeah, so, oops, there's the button. So there's an N here, there's an N there, there's an N there, but it's crossed out. What they were trying to do was come up with different forms of evidence to figure out whether or not this faint fuzzy thing was a system that was far away and therefore very large and a galaxy in its own right, or was it something more nearby? Could it be a solar system in the process of forming or something? Hubble was finding novas. That's what the N stands for. So these were stars that appeared and then disappeared, faded away. Now we've known about novas for a long time. They happen essentially what appears to be at random all over the sky, although more often towards the Milky Way. We now know that these are systems of stars where you have a white dwarf and a companion star, and the white dwarf takes off material and has a thermonuclear explosion on the surface. They didn't know that at the time, but they did know that they sort of happened all over the sky. But here we are looking at a very narrow part of the sky, about maybe the size of a little bit smaller than the full moon probably. And there's 3 of them all at once. So that Hubble was using as an argument to say this is its own galaxy. That's why you can find so many novas in one place all at the same time. But one of those novas came back. So one up here, right, the buttons here, this guy up here came back, and then it went away, and then it came back and it went away. So very excitedly in red, he crossed out the N and wrote in var for variable, and specifically a Cepheid variable. You have to follow it over night after night after night. There's lots of different kinds of variable stars out there, but Cepheids have a very peculiar way that they rise very quickly and then sort of fall off slowly. It almost kind of looks like a shark fin if you plot up the brightness as a function of time. And then you measure what the period of oscillation is. You use Henrietta Leavitt's relationship, and then you can figure out the relative distance to that Cepheid compared to a Cepheid, let's say, within our own galaxy. Can you see the Cepheid? Maybe if we zoom in a bit. Yeah, can you kind of see it? Yeah, a lot of squinting going on. I've actually looked at the original with the magnifying glass. You really gotta look hard. And in fact, it's often very amazing to me that Hubble was able to see it all. That they knew these fields intimately. They've been looking at them night after night after night after night. This is the largest telescope in the world. It's a 45-minute exposure, and it's just barely detectable. It's far away. If you want to know what would the Cepheid have looked like if it was, say, 8 kiloparsecs away, our distance from the center of the galaxy, it would have looked that bright. Okay. So even before he applied Henrietta Leavitt's relationship and did the distance and everything like that, he knew, I'm sure, this is far away. So that solved the debate. But that's just working with photometry. That's just taking imaging of the sky. Oh, and I should point out that that was taken on October the 5th, 1923. So 99th anniversary 2 days ago. It's the 7th today, right? Yeah. And so next year, it's going to be the centenary. So we're going to have a party. Okay, well, so that's one way to figure things out, is to look at imaging, and you can use Cepheid variables and stuff like that. But we've got another trick up our sleeves, in our astronomical toolbox, and that's spectroscopy. So you take a slice of this star, you put it through a prism or bounce it off a grating or however you want to do it, and you split it up into its component colors, and you see a spectrum. So if you've not seen a spectrum before, I mean, it looks basically a rainbow is a spectrum, is taking the light of the sun and spreading it out into its colors. If you look very closely at a solar spectrum, which you can do if you come up here on the weekend and the SNO telescope is open, we actually can show you the solar spectrum, and you can see the Fraunhofer lines, those dark lines that are due to absorption by elements in the atmosphere. Here, this is just a spectrum of a star. I don't think it's actually that star, but it's just a sample. And you can see it's got a characteristic shape and these lines. These are just elements in the atmospheres of the stars stealing very specific wavelengths of light. But you do the same thing with that quasar and you see something completely different. This thing peaks here around, in sort of the greenish part of the spectrum. This one is still going up way into the blue and probably into the ultraviolet. This tells you immediately that this thing is much hotter than this one. Also, these are absorption lines. These are emission lines, different physics going on entirely. And more importantly, there's a very prominent line here called H alpha, and H stands for hydrogen. It's labeled right there too. And this is essentially one of the strongest lines that hydrogen makes. And you can do that in the lab. You can figure out what the wavelength or frequency of that is, and it should always be the same, right? Atoms are atoms, physics is physics, and yet that one is not where that one is. It has actually been redshifted. And I'm sure all of you guys know exactly what's going on there, but in case you don't, redshift is simply the Doppler effect. Any wave phenomenon, if you're traveling toward or away from the source, the wavelength of that wave is going to shift to higher frequencies or lower frequencies. Same is true with sound. That's why you hear, a race car going. In case of light, it's color. And this is from a paper by Milton Humason, who was Hubble's assistant. And it shows galaxies. You can probably tell this one's closer and that one's probably farther away. And here is the spectrum in sort of black and white. And these lines on top, those are comparisons. So those lines stay in the same place. That's the element that you put in the beam so that you can do a wavelength calibration. But the calcium H and K lines, as you can see, are shifting more and more and more to the right. And so this allows us to measure the actual speed of a galaxy. So the more there's a shift, the faster the galaxy is going. And if it goes to the right, it's a redshift, which means it's going away from you. If it goes off to the left, that's a blue shift, and it's coming toward you. And the crazy thing is, all right, there's a few galaxies that are blue shifted, including the Andromeda Galaxy. In fact, it seems to be on a collision course with us. But every other galaxy in the universe is going away from us. And this was pointed out by an astronomer at Lick Observatory named Visto Slipher, even before Hubble came out with his famous result. All galaxies appear to be flying away from us. That's not good. That makes us seem like we're in a really special place. But Hubble added distance into the analysis, right? So Slipher had the velocities, but Hubble had the distances thanks to these Cepheid variables. However, the Cepheids only get you out about that far. A lot of the time you see this image and say, oh, look at all these distances. Those were determined by Cepheids. Not true. These ones were determined by Cepheids. These ones over here were determined by looking at the brightest star in a galaxy and assuming that the brightest star in any galaxy is the same brightness as the brightest star in any other galaxy. Very similar to a method I'm going to talk about in a second called the tip of the red giant branch, but you calibrate these distances using those Cepheids, and that lets you get a little further out. And then these last ones out here, those are in the Virgo cluster. And then you have to use even different techniques to get the distances to that. So there's a lot going on in this diagram. It's not so clear cut that you've got the distances from the Cepheids. There's other stuff going on. And the other thing is, This paper is not about the expansion of the universe. It's not about cosmology. It's Hubble using galaxies, which he now knows are very distant, as a frame of reference for determining the motion of the sun in our galaxy. So these were being used kind of as your zero frame of reference. And if you measure your velocity relative to all those points, you can figure out which way you're going. And that's when he saw that there was this trend that the more distant he used, the more distant galaxies he used, the frame of reference seemed to be different. And so that's why he drew this graph. He finishes his paper off with this statement. The outstanding feature, however, is the possibility the velocity distance relation may represent the de Sitter effect, and hence that numerical data may be introduced into discussions of the general curvature of space. Curvature of space, not expansion. He did not believe that he had measured expansion of the universe. He thought he was seeing something from a solution of cosmology that de Sitter had made for a static universe, which ended up actually being not correct. So Einstein had a static universe. He put in the cosmological constant to balance gravity with anti-gravity, but it turned out later that that's an unstable solution, and anyone sneezes and all of a sudden the universe will expand or collapse. De Sitter also had a static universe, but he did it in these weird coordinates where everybody who's making observations are accelerating for some reason, some phantom energy or something like that. So again, it wasn't the right solution. The right solution for Einstein, Einstein gave you the theory. Now you have to figure out how that theory applies to the universe. And the one who did it correctly first was Lemaitre. And if you've never heard of Georges Lemaitre, he was a Belgian priest and a physicist. And he correctly made a model of an expanding universe. In fact, he showed that de Sitter's model clearly was incorrect. And not only did he make it a solution for an expanding universe, he took Hubble's distances and Slipher's velocities, and he properly cited Slipher for the velocities, which Hubble did not, and came up with the Hubble constant. Although it wasn't called the Hubble constant at the time, it was just a rate of expansion. He came up with 625 kilometers per second per megaparsec in the year 1927, which is 2 years before Hubble's paper came out. However, it was published in French. And so the American astronomers were likely not aware of it. Oh well. 1931, it was translated into English and published in the monthly notices of the Royal Astronomical Society, with the Hubble constant strangely missing. Everything else was in there, but his estimate of that was gone. And there was all this conspiracy theories about Hubble pressuring the editors of the journal that they wouldn't include it. But it turned out actually when they found some correspondence between Lemaitre and the editors that he said, I know I'm not going to put my value in, Hubble's is better. So, we'll just leave it at that. Now, it also, an expanding universe fixes another problem that we're kind of somehow special, that all the galaxies are moving away from us, which is kind of weird. So here's a demonstration. This is from a demonstration we used to use with overhead transparencies. Remember those things? Yeah, we don't have those so much anymore, so we'll just use power or keynotes abilities. So here's a double Hubble deep field, black and white. I can expand that by 10%, okay, to simulate the expansion of the universe. Now we can make that transparent, and now you can see the old universe with the new universe. And hopefully what you can see is that here we are at the center, and all the galaxies appear to be moving away from us. And if you look at this galaxy, it only goes a short distance, but this galaxy out there goes quite a long distance. So that explains simultaneously why all the galaxies appear to be going away from a single point, and why the farther away you are, the faster things are going. And if you choose any other galaxy, let's say that one, so if you're living in this galaxy, well, you see exactly the same thing. Everything appears to be going away from you, and the farther away it is, the faster it's going. So we're not at the center of the expansion. Everywhere is the center of the expansion. So we're not special, or everybody's special, however you want to look at it. All right, so back to this. Here we have this Hubble diagram. Now, once you apply Lemaitre's solution, you can now actually make predictions. What's the universe going to do? What did the universe do? And in particular, if you take the slope, which we now call the Hubble constant, the rise over the run, which is in units of kilometers per second. By the way, the per second is missing from this graph. Per megaparsec, if you take 978 and divide by that number, whatever that slope is, that roughly gives you the age of the universe in gigayears, billions of years. And as you can see, if you put in Lamite's value of 625 or Hubble's value of about 500, anyone see a problem? You get a universe that's kind of like 2 to 3 billion years old, and the Earth is 4.5 billion years old. Slight problem there. Well, as usual, there was a problem. There's not just one kind of Cepheid. There's two, at least, kinds of Cepheids. There's a population 1 and a population 2 of Cepheids. Once you discover that, which was discovered by a Carnegie astronomer by the name of Walter Baade, your Hubble constant up here of 600 to 500 now shrinks down to about 100. Well, plus or minus. There were astronomers who very, very strongly believed it was 50 kilometers per megaparsec. Alan Sandage, another Carnegie astronomer who loved Mount Wilson, did a lot of observing up here. He believed it so strongly that he had a license plate that said H0 50. But you had other astronomers who believed it was 100. I call that the not quite so great debate. And lots of stuff in between. There's a lot of, variation going on there. And to this day, it's still going on. What is its value? Even ended up being a question on Jeopardy. And Wendy Friedman is an astronomer. She's now at the University of Chicago, but she was the director of Carnegie Observatories. And more to the point, she was the principal investigator for the Hubble Space Telescope Key Project. So when the Hubble Space Telescope was designed, they had certain key projects in mind, one of which was to measure the Hubble constant. And so this is the Hubble diagram, and these are all Cepheids. Okay, so not only these ones being Cepheids and using other techniques. This is all Cepheids using the really great angular resolution of Hubble to be able to see the actual Cepheids far enough away and measure their brightness. And just for reference, that's where Hubble's diagram, his entire diagram fits. So his Cepheids were only out to like there. So much progress. The other thing you may notice in this diagram that was missing from Hubble is these very important things. Those are called error bars. Those give you an idea of how certain you are that that point actually lies there. And so now, if you saw that point just by itself, you might think, well, what's going on with that? But you'll notice it's got a nice healthy error. So, oh, okay, here, but just because of some uncertainty that we're not quite sure what it is, it can end up down here. The eagle-eyed people may notice, well, wait a minute, I thought velocities were really easy to measure, right? You measure a redshift. Isn't that easy? And why? And the distances are supposed to be the uncertain thing. Well, that's true. It's easy to measure a velocity, but it's maybe not so easy to interpret a velocity. So let's have a look at this. This is Stefan's quintet. Imagine you have a group of galaxies, okay? Well, they all have gravitational pulls on each other. And so they are going to have a group velocity. They're bound as a group. So as a group, they're going to be moving thanks to the Hubble expansion. But each individual galaxy will have its own random velocity in that group. And so if you choose any one of these as your galaxy to figure out distance and velocity, well, okay, there's the Hubble velocity, but there's this velocity. When you add them up together, they kind of cancel out. So you may end up with a point that's too low. Whereas if you picked this guy, okay, now these two velocities are going to add together. You're going to get something that's too big. And now that point's going to be too high in the Hubble diagram. And this is something you really just can't get away from. Some of these galaxies are just going to be moving. And if they're moving at velocities that are comparable to the thing that you're actually trying to measure, it's a problem. So what you really want to do is you want to go farther away, because the farther away you go, the larger that Hubble expansion velocity will be, but the other velocities basically stay the same. And so now it's going to be easy to measure that effect. Unfortunately, if you try to move farther away, your fields get more cramped. They get more, the stars appear on angular size to be much closer together, and it's harder to pick out a Cepheid in there, separate it out from all the rest of the stars. You have to be able to measure the brightness of the Cepheid by itself with all that other light coming in from those other stars. And that sets a limit, which is why JWST is actually so, exciting, because it's going to have better angular resolution than Hubble, which means we can do this further out. But we've only just gotten JWST, so what did we do in the meantime? Well, it turns out there's another thing out there, like a Cepheid variable. It's a standard candle. It's a white dwarf being with hopefully a companion. There's other ways of doing this, but companion around a white dwarf shows what's going on. I told you before there were novas that have thermonuclear explosions on the surface of the white dwarf. Well, it turns out you can also have situations where you push the white dwarf past something called the Chandrasekhar limit, which then allows the entire white dwarf to thermonuclearly burn up to nickel 56 in seconds. And so this is a type 1a supernova. So you imagine this is slowly building up to that magic Chandrasekhar mass, which is 1.4 solar masses, and kaboom, the white dwarf's gone. You generate a whole ton of nickel 56, which then radioactively decays into cobalt and then radioactively decays into iron. We call these iron bombs, and probably most of the iron in your blood actually came from a type 1a supernova, or several. But if you think about it, you're sort of bringing something up very slowly to some magic mass. Sounds like it could be a standard candle, like it would do the same thing again and again and again. It turns out it actually is. I'm going to show you, this is an animation, because when I show you a picture of a supernova, a lot of people say, well, that doesn't look so super, because it's so far away and there's other stars in the field and it's hard to see what the supernova is. But here's an animation I made using this program called Space Engine. If you haven't used Space Engine, it is a lot of fun. So you can basically go anywhere in the universe. If it has data, it will show you that. If it doesn't, it will randomly generate physically good data. So we're going to zoom in on a galaxy, NGC, 1316, I think. It's a bar spiral, yeah. There. Now, the supernova is somewhere there, but it's not really completely obvious where. So let's go outside the galaxy, get rid of all those pesky foreground stars, and there it is. All right, so now it looks a little more impressive, right? You can't see any other star in that galaxy. They're too bunched together. It's just a haze, but you can pick out a type 1a supernova. And and then it fades away. And that's really important. Unlike a Cepheid, it doesn't come back. It fades away and it's gone for good. There's the real image. NGC, it's 1365. Okay, it goes away. So I can come back years later, take an image of the same field again, and now through the magic of CCDs and pixel by pixel math, I can simply subtract one image from the other, and all that's left is the supernova. So you would not have been able to tell that there was a supernova hiding, in that galaxy. But after doing the subtraction, it comes out very cleanly. You've gotten rid of all the other starlight, and so it's a very clean observation, and you can measure the brightness of this. By the way, you might see this little white thing. That means there was something in the original, in the other image that wasn't in the original. That's another supernova that went off. That one's 2011 IV. This one's supernova 2007 ON, which we had also observed. So we already had a image to use for subtracting the field, but because the supernova is in it, it ends up being negative. Yeah.
When you see the type 1a supernova with the standard candle, how much does metallicity impact and move out the color?
Okay, so for those who are on Zoom, the question was, when you use type 1a supernovae, how much do you have to take into account the metallicity of the progenitor star? And how do we calibrate that out? The answer is probably, and we don't know. So remember, this is a white dwarf. So that white dwarf evolved off the main sequence a long time ago and has probably been sitting around for a very long time. And so we don't know currently a good way to measure the metallicity of the progenitor. We can measure the metallicity of the galaxy. We can measure the metallicity of the area around the supernova. If there's gas, we can get a gas phase metallicity. But how that relates to the progenitor's metallicity, it's very unknown. And so we do take into account metallicity, but it's not clear to me that it actually helps at all. But as you go back further and further into the universe, you're going back further in time, you're going back to a time when stars on average had less metallicity. This is a possible systematic that we still don't know quite how to deal with. You can't measure the metallicity easily of the supernova itself, because by the time that happens, so much nuclear synthesis has gone on that whatever the metallicity was originally is completely gone. All right, this is what a light curve of a type 1a supernova looks like. It rises, reaches a peak, and then decays. And these decays are very characteristic. They're exponential decays, and that's because this is all the radioactive decay of nickel 56 and later cobalt 56. So what powers the supernova light that you see is radioactive decay, which I thought was pretty cool when I first discovered that. I couldn't give this talk without showing you this latest one that we just found, supernova 2021 AEFX. Okay, the title's sort of hidden behind the Zoom thing. Remember before it was supernova 2007 ON and supernova 2000 whatever AB, because what you do is you start with the year and then you start with A, B, C, D, E. When you run out of letters in the alphabet, then you double up the letters, A, B. We're now finding so many that we now need 4 of these. And it's thanks to things like the Zwicky transient factory that runs on Mount Palomar, that is scanning the sky once every 2 or 3 days. They're finding so many that we have to actually start naming them with these crazy numbers. And here is our light curve. And as you can see, we caught it extremely early. And it's not obvious from here, but we were actually observing it twice or even 3 times a night, and we could see it getting brighter just during the course of one observing night. So it was crazy. So we've observed this as much as we could, except when it went behind the sun, then you really can't do anything, but then you wait and it comes back again and you can keep on going. Yeah, question.
The x-axis value is that east or west?
Those are, oh, sorry, the question is the x-axis, what units are those? Those are days. Yeah, so this is up to 160 days. I think we're now up to 300 and, well, it's 2021, it's 2022, so 365 days-ish, something like that, yeah. And just like with Cepheid variables, there is a period luminosity relationship. This was discovered by another Carnegie astronomer by the name of Mark Phillips. Essentially how long they last. Some of them go up and come down very quickly. Some of them go up and come down more slowly. It turns out that the slower they are, the brighter they are. So there still is some kind of effect. They're not perfect standard candles. More importantly, there's this stuff called interstellar dust, which you may have heard of. And interstellar dust makes things dim, which is terrible for us because dimming is what we're interested in terms of distance. If there's also something making it dim, that's bad. But it also makes them redder. So as long as you can measure how red they are, you can calibrate that out. So there's an effect of how long they last, and there's an effect of how red they are. But it turns out if you work in the near infrared rather than the optical, that relationship here for how long they last is nearly straight. So it's almost a perfect standard candle. And as you probably know, dust is a very strong function of wavelength, which is why it makes things red. And the redder you go, the less extinction there is. And so working in the near infrared, it's practically a standard candle too. So near infrared, good. So we, whoops, I didn't want to go quite that far. Oh, it's okay, I can tell. They're great. Supernovas get you a long distance away. The problem is the last time we had a supernova in this galaxy, for which we could maybe get some independent distance estimate to it, was in 1600 and whatever, and that was Kepler's supernova. We're waiting. They're supposed to be every 100 years or so. We're well overdue. Maybe Betelgeuse, but that's going to be a type 2. We need type 1As. So we don't have any supernovae for which we can get a distance to directly. We have to use Cepheids. So we have supernovae that were in galaxies that were close enough to have a Cepheid distance. So the Cepheids tell us how bright they are. So we have this thing called a distance ladder. Solar system, we use radar. Closest stars, we can use parallax. From there, we can calibrate the Cepheids. That gets us out to about 40 megaparsecs. And from that, we can calibrate the type 1a supernovae. So you may have heard this called the distance ladder. It's rickety. It's prone to error. Could collapse at any moment. So anything I tell you, keep in mind, if all of a sudden the Cepheids tell us something different, the whole game changes. So we began about in 2004. We started what's called the Carnegie Supernova Project, and this was to do a really good job at measuring type 1a supernovae in the near infrared using the facilities at Las Campanas Observatory. Here is a rogues gallery, Wendy Friedman, part of the group. I'm behind her. Mark Phillips is in there somewhere. Yeah, there's Mark. Nydia, I will point out because she's been on the mountain and has used every single telescope and every single instrument. And when the COVID-19 hit and they weren't allowing anybody on the mountain except those who could, already use the telescopes, she was up there every night. She observed for us for 2 months straight. Yeah. Here's today's, this is a smaller group meeting, but I wanted to put this one up because I wanted to point out my postdoc, Shuvo Uden, who we hired about 6 years ago. He's now gone on to Texas A&M, but some of the stuff I'm going to be showing you is directly his work. So I wanted to give him credit for that. We do all this again at Las Campanas Observatory. We've got the twin Magellan telescopes here. They're 6.5 meter telescopes. And over there is the DuPont and our little swope. The DuPont is 100 inches and the swope is 40 inches. The swope actually does most of the imaging. So you might think, wow, hey, wait a minute, didn't you want to use the 100 inch? Well, yes, 100 inch is harder to get time on. And these supernovae are very bright. You don't need a 100 inch telescope. We're not looking for tiny little Cepheids. We're looking for bright supernovae. So they can do all the work for us. The DuPont 100 inch telescope we use more for spectroscopy to make sure that we're looking at type 1As and getting the redshifts of those galaxies. That requires a little bit more glass. So here's that Hubble Space Telescope key project. And I'm going to show you what our Hubble diagram looks like in comparison. The type 1A gets you much further out. So out to about 300 megaparsecs. But again, you need those Cepheids to set the 0 point of your distance ladder. And there was our values. I published this in 2018, so we got about 73 plus minus, a couple. Very close. A little bit, yes, yes. And that takes you to about 1 billion light years outwards.
So Hubble's original plot is just a tiny dot.
I didn't even bother. This is the one I was promising you. This is only a few days old. This is the Carnegie Supernova Project 2. Where we decide, you know what, the swope could get us certain far, but hey, let's use that 100 inch to go even further. So as you can see, we're now twice as far away as we were before. So that's where our first Hubble diagram got us. Using the DuPont 100 inch telescope got us further out. Now I put up 2 lines there. The red line, this red line is a best fit. But you may notice that what's going on with all these points down here? They seem to be lower down. Does anyone have a guess as to what's going on? No, it's not the Cepheids. So 600 megaparsecs, 1 billion, so about 2 billion years ago. Yeah. What you're seeing here is the acceleration of the universe. So you're looking at a time in the past that's long enough ago that the Hubble constant was different because the universe has been speeding up ever since. So the green line is taking that into account as well. So we actually managed to measure like the other cosmology part of this as well, which was surprising to me, but it actually works. So here's the results of, we've got the original Hubble Space Telescope key project gives about 75 for the Hubble constant. This is my 2018 result, very similar to another one that Adam Rees of Nobel Prize winning fame got. And the big crisis in cosmology, that thing that everyone's been talking about, is the gap between this and this. This is measured at the cosmic microwave background and also using something called BAO, which is baryon acoustic oscillations. I don't have time to go into all that, but essentially think of this as early universe measurements of the Hubble constant. This is late universe measurements of the Hubble constant. And it's not so much this is a gap, but the gap is so large compared to those error bars. That's what the crisis in cosmology is. But you wonder, Cepheids, oh, dang Cepheids. Well, maybe, is there a better way? Could we do it in a different way? Well, yes, it turns out you can. Just like Hubble used this technique of looking at the brightest star in a galaxy and assuming that all galaxies have brightest stars of the same brightness. Here we do it a little bit more intelligently. We look at the Hubble, the Hertzsprung-Russell diagram. If you don't know what an HR diagram is, don't worry. Essentially, you look at the color of a star and how bright they are, and there's a very definite tip of what's called the red giant branch. These are the red giants in the galaxy that are evolving, and they reach a certain maximum brightness, and that turns out to be pretty good as a standard candle. It's got a lot of other advantages over Cepheids. In particular, you can do it way out in the outer field of the galaxy where things are much less crowded. Cepheids, you got. So what you can do is you can take your distance and get rid of the Cepheids and put the TRGB, the tip of the red giant branch, in instead and say, hey, do we get the same answer? What do you think? Do we get the same answer? No, of course not. All right, so where does the TRGB send you? Okay, halfway between. We didn't make any friends. Nobody was happy with us. So barely consistent with that and barely consistent with that, you had to know it was going to happen. And since there have been other things, we have this other technique called the surface brightness fluctuations, another way to get distances to galaxies. That gives you that answer. Gravitational lensing, as you heard in the previous talk, you can do time delays, and that gives you distances to galaxies. You can use that to figure out the Hubble constant. But here are two groups doing the same thing and getting somewhat different answers. And then, of course, there's the gravitational wave, that neutron star merger. Turns out you can get a very good distance to that, and you can use it to measure the Hubble constant, but with very large error bar because it's only one event and it was very close by. It didn't tell us anything really. And drum roll, the latest from my postdoc, Shuvo. What he decided to do is take the Cepheids, the surface brightness fluctuations, and the TRGB and combine them together into one big data set and ask the question, how wrong could the answer be to make it all make sense? And there's your answer. So it really does kind of cover those cases. So is the tension real? Is the crisis real? Is it really a crisis? I'm going to say I'm leaning to no. It's looking more like there's a systematic error between Cepheids and TGB and surface brightness fluctuations and whatever else. But I'm not 100% sure because this is very preliminary. Like I said, we haven't published this yet. We're days, hopefully, which usually means weeks, away from hitting that submit button, and then we'll find out from the community what they think. But there's more to come because, as I said, James Webb is going to be much higher. They can see those Cepheids to much farther distances. And then we have these larger telescopes, the GMT, the TMT, the European large ELT, and they can do the same thing. They've got this stuff called adaptive optics, which lets them look at much farther things away, and they'll have more surface collection power, so they could potentially even see further away. So it may be that type 1a supernovae aren't needed at all. Maybe we'll be able to see Cepheids all the way out to whatever distance. Anyway, that's all I have to say. So I'm happy to take questions. Yeah.
What interested you in coming to astronomy?
Okay, the question is what interested me in going into astronomy? So I started out with, I was born in '72, and that was still soon enough after the Apollo missions that there was still a lot of that in the public consciousness. So I grew up loving the Apollo missions. I had books on Apollo. I had the little lander model and the Saturn V and all that sort of stuff. And very quickly from there on, you get into, well, what is space? What is the moon? Where'd the moon come from? How far away is that? And then very soon you end up with answers, certain questions your parents don't have answers for. So they got me a subscription to Astronomy magazine, yeah, I think it was Astronomy. And of course, you get that wonderful sky chart in the center. So I got a pair of binoculars and started looking for things. And then when my dad saw me out, freezing my butt off with these binoculars, he said, okay, this kid needs a telescope. And so at age 12, I got a telescope, and that was it. I was hooked. Does that answer the question? Great.
What was your first telescope?
My first telescope was a 4-inch Newtonian from some company. I couldn't even remember. It wasn't Orion. It was, I have to go back and look.
Better than a Montgomery Ward's.
Yeah, it wasn't like, something from Canadian Tire. It was actually a proper telescope. My father, he was a professor of history, but he knew the physics faculty, and he did his homework and asked them their advice, and they gave him some good advice. So I still have it. It really needs to be recoded, but it still works. So.
How did you collimate that back then?
I didn't even know what collimation was. It worked enough for me to see the Orion Nebula, and that was enough. And then later on, I got something, I got into it more, and then I learned how collimation worked. And my wife's also a really big amateur astronomer. So she had one of those laser collimators. That's why I fell in love with laser collimators. Question. Okay, the question is, what research am I focusing on now? That goes back to that other supernova I was showing you, 2021 AEFX. I am kind of sick of the Hubble constant. You take 10 years of observations on a telescope, night after night after night, light curves, doing all the analysis for a number, one number. I had the mistake of actually saying to a rather prominent astronomer who works on the Hubble constant, well, it's just a number. The fact that there is a number is interesting, that you can have an expansion, that's cool, but the exact value, now that I know how many ways things can go wrong is just enough. You do the science, you make discoveries, but if you're just working on making those error bars smaller and smaller and smaller, it really grinds you down. So what we're more interested in now, along the way, while we were doing this work, you'd find supernovae that didn't quite fit in with the categories that you had established. It was a type 1a, but it was weird in some way. It had weird lines, odd amounts. It was missing sulfur. It was too red. It was lots of different things. So we wrote lots and lots of papers about the weirdos, we would call them. And it turns out when you have the weird things, it pushes the physics in different directions that you might not have thought of before. Type 1As, they're boring. Everyone knows basically how they work, not exactly how they start, how they explode. So that's still an interesting question, but the physics of radioactive decay is very well understood. But the weirdos were giving us puzzles that we'd never seen before, and it let us do physics that I thought of before. And so we thought, maybe we should just have a project that's entirely about going after the weirdos. Unfortunately, they're very rare. And so you really can't put a project together just based on very rare events. And so the other idea we had was, we're very good at following these things after they've gotten to their brightest peak, but we don't have a whole lot of data down here. And it turns out, if you want to know what the progenitor was like, was it 2 stars? Was it 2 white dwarfs that hit each other? Was it a white dwarf and a massive red giant? All these sorts of things. You'll want to measure these events early, before the fireball has consumed everything and it's just, radioactive decay after that. And so we started this thing that we're calling POISE, which is the precision observations of infant supernova explosions. We're poised to observe. That was the idea. We also wanted to use poison, but we thought maybe that wouldn't work so well. The idea is you want to get on these as like hours after they explode. And that's tough. That's really hard to do because the time between discovery, classification, and then follow-up is usually on the order of tens of days. So we are going after everything now. We don't wait for classification. If it looks real, we're on it as fast as we possibly can. And that requires a special kind of observing called target of opportunity, which means you get this time on, say, like Gemini, you can interrupt whatever's going on at that point and do your observations. It's extremely hard to get. So we're still working on it. But yeah, we managed to get on this one very, very quickly because it's so nearby, so bright. With our 40-inch telescope, which we have a lot of time on, we were able to jump on it within, a day or two. So that's what we're doing now. Yeah.
The bar maybe showed like there are a lot of ends in the Andromeda.
Yep.
I'm curious, like, how many nights you spent to find those supernovas in Andromeda? Because as you mentioned, you guys have like 400 years.
Oh yeah, okay. So the question was, given looking at the VAR plate, all the novas that Hubble found, how much time did he have to spend to actually find those novas? When in fact, we expect novas to happen once every 100 years or so, right? So supernovas happen once every 100 years. Novas happen on a much more regular thing. Still, it's not every year that you find a nova, so they're still relatively rare. But the thing you got to remember is we're inside a galaxy, and the novas are happening around us. And if two novas happen at the same time, but that one's 500 light years away, and that one's 100 light years away, there's still going to be a difference of 400 years between when we see them. In fact, because the galaxy is 100,000 light years across, and we expect supernovae to happen roughly once every 100 years or so, there are probably 1,000 supernovas that have happened already, but the light just hasn't gotten to us before. Whereas when you're looking at the VAR plate, you're looking at the entire galaxy, and all that light is coming to you at once. So it's a slightly different situation where these things happen. How often he was looking at Andromeda, I mean, he was probably looking at, I can't imagine how many times he looked at that galaxy, but it must have been for years. Yeah, lots and lots and lots of time spent on that. But that one VAR plate had 3 novas that he identified. Now you'd have to follow that night after night after night and watch them disappear to identify them as novas, or have them come back and see them as Cepheids. So there's a lot of observing time that has to be invested to figure all that out.
Do we count the plates in the vault?
The question is, can we count the plates in the vault? The answer is, you can. We actually have a volunteer did catalog all the plates in our vault. So we keep all the plates that were taken. And they're in our basement and behind a big, huge vault. And only recently, within the last, I think, 7 or 8 years, we had a volunteer go in and catalog all of it. So you can search online, our database, to see what was observed, how many times, and when, and by who, and all that. We still have not yet digitized. That's a lot more work, but it's there. And so if an astronomer somewhere needs that data, we can then digitize one, we can digitize them on demand, but we just haven't done the whole thing yet. Do we probably want to get on to the next talk, right?
Probably do. Okay. But I did want to know a little bit more about Wolf-Rayet stars and when they go supernova. This is a rare occurrence, correct? Yeah. So there's still some. Okay. So the question is, what about Wolf-Rayet stars and when they go supernova? So the Wolf-Rayet are believed to be sort of like the most extreme high mass, where the stellar wind is in fact blowing off a significant fraction of the outer atmospheres of the star. So there are type 1a supernovae. Now type 1, Roman numeral 1, means no hydrogen in the spectrum, which is why we think white dwarf is, because white dwarfs don't have hydrogen. But there are all these other ones called type 1b's and type 1c's, and the 1b's and the 1c's don't seem to be white dwarfs. Those seem to be high mass stars that go what we call core collapse supernova. That's when the core runs out of fuel, the whole star comes crashing down on top of it, it rebounds, and you get a supernova. The type 1c's are probably Wolf-Rayet stars, where the hydrogen is just gone. It's been blown away, and so all that's left, in fact, no, those would be the 1b's. For the 1c's, you also have to get rid of the helium, so you'd have to go even more down. And that one's
harder to do. And there's another way that you can do that is if you have a companion star, which is pulling off. Yeah, so when you get a red giant and it fills its Roche lobe and you start getting this leaching of material off, or a combination of both. Maybe you get these stars with big stellar winds with companions that gather up the units. There's a lot of stuff we're not quite sure about. And again, that's why we're doing this program where we're trying to get these things really early so we get something like, for instance, if there was this massive amount of stellar wind throwing off that hydrogen, well, it's still there, it's still hanging around. And if you get the supernova early enough, you can get where that light shines on that hydrogen, ionizes it.
It's a
Shell, exactly. And you get this narrow hydrogen line, which then recombines and then produces its own radiation. And you can see that as a signature, but you got to get it early. Yeah.
LSST will obviously you get a lot of supernovae. However, it would be we would survey like every 3 months. Will that be quick enough cadence to be useful for your study?
Yeah.
Or will it be able to have enough limiting magnitude to go back and be able to look at the projection before?
Right. So the question is about LSST, Large Synaptic Survey Telescope, also known as the Vera Rubin Observatory. And they're going to have a larger aperture, but a shorter cadence, longer cadence, so every 3 nights. And will that be useful for what we're doing? And also going back and stacking all those images, getting a very deep image and trying to find the progenitor, correct? Yeah. Yeah, so the LSST or the Rubin Observatory, the design of that experiment has changed a lot over the years. You have a lot of different interests who are competing to get just the right configuration for their science. And so in some ways, LSST had to compromise. And there is sort of a short cadence, but narrower part of the sky. The wider part, whereas the whole sky, I think, is only 5-day cadences. I think I haven't looked at it very recently, but there is trade-offs. Like, do you go fast and narrow, or do you go slow and wide? So yeah, for us, it's not going to be the best way. The one thing that's really good about it is it's in Chile. Right now, we get most of our observations from ZTF, which is on Mount Palomar Mountain, sorry. And they're in a time zone that is west of our observatory in Chile. So we're all ready to observe, but the sun hasn't set for them. And so by the time they're on the sky and potentially finding candidates, it's getting late for us. And so that timing isn't great. Whereas LSST will be in Chile, same time zone. So we're on the same clock. But even better is another survey called ATLAS, which is John Tonry's project. He's looking for primarily Earth-killing asteroids. That's the main point, but you're looking at the sky on a rapid cadence. They're actually going to be in South Africa and a few other places around the world. And that's east of us. So that's even better. They'll be finding candidates, and then we'll be all set to follow them up when it gets dark for us. So that's the one I'm really looking forward to, is ATLAS. They also have one in Chile. So I think we're going to probably get more from them than we will from Rubin. Yes.
How are the satellite mega constellations research?
Yeah. So the question is, how are these mega satellite constellations going to affect? Well, not great. They're not going to help, obviously. They're mostly a problem during twilight and the early hours of the night. So if you're just interested in doing supernova studies, it's not so bad. You lose some of your night, and just chances of false positives are much higher, obviously. But if you're us and you're trying to get on that as absolutely quick as possible, and you got to wait for all those satellites to no longer be a problem because now the terminator of the Earth has moved far enough west that you don't have to worry about it anymore. It's more time that we don't have, but you know, we're going to have to live with it because I don't think we're going to get rid of them. The other problem is because you can imagine, well, if you do multiple exposures, you can do median filtering and stuff like that. The real problem is with the very bright ones, they can leave ghost images if you're working in the infrared. If you've got these infrared detectors, really bright streaks, they leave ghost images for hours afterwards. There are bright ones, and if you've got a big telescope, even the not so bright ones are going to be a problem. So having software that can tell us reliably when these things are coming through our field is going to be very important, especially for the big telescopes. Yeah. Yeah.
Is there any existential threat that you see from the universe that possibly beyond asteroids?
Oh, wow. Okay. Question is, given the success of the DART mission, is there anything that I know of or that I feel is a threat to us other than asteroids? Comets. The comets are the scary ones. Asteroids, yeah, you've got, hopefully, if you can catalog and find them all, get good orbits, go into the future, yeah, you could see, oh, that one in 100 some odd years is going to come close. Let's give it a nudge, take that away. But those Kuiper belt, the Oort cloud comets, they come out of nowhere. And the nightmare is they come along a path that's close to the sun. You never see them, and there's no chance. So that's what I feel is the biggest threat, is the comets from the outer parts of the solar system just coming in. Yeah.
And what about nearby supernova explosions?
What about nearby supernova explosions? No, I don't see any problems there. We don't have any white dwarfs near us that we can see that are candidates for type 1As. And the type 2 candidates like Betelgeuse, Eta Carina, and they're far enough away that I think I made the calculation. If Betelgeuse went supernova and was a typical type 2, it would be about as bright as the full moon. So it's bright, but it's the one that might be that you can worry about are gamma ray bursts.
Yeah.
Gamma ray bursts, those ones are highly beamed, we think, and are extremely powerful. And
is that from a pole that it's ejected, or?
Yeah, so it's what's probably happening is you've got a star that's so massive that the black hole forms long before the supernova happens, and basically the black hole eats the star from the inside out, and then you just get these jets of relativistic material and gamma rays and everything like that. Good news is those kinds of stars probably really don't exist anymore. Those are like supermassive stars that were probably only possible when the universe was much lower metallicity. So I think we're away from that, but there are people who have postulated that some of the extinctions that we've seen could have been caused by gamma ray bursts. And in that case, half the Earth would be incinerated and the other half would be okay, I guess. But yeah, move on. All right, well, thank you. Great questions, by the way. Excellent questions.
Thank you. Okay, so for our final speaker tonight is going to be Mr. John Schwartz. John is an old friend of mine, a very enthusiastic amateur astronomer, has done a ton of outreach. He loves big scopes, he loves good optics, and I think a lot of amateur astronomers that have met John don't know how much of a artist he is and how good he is at drawing at the eyepiece. And so he's going to show some of his work tonight, which I think is great. Certainly there was a time when there was no photography and everybody drew at the eyepiece that was an astronomer trying to record data. But I think John has taken it to like another level, okay, which is really cool. So I need to pull up his program. I'm going to stop sharing here. I feel a little bit like Chris Burns here controlling his presentation. Here we go. Chris, do you want me to erase this so that I don't like use it, or? Because I will use it.
Don't use it for 2 weeks.
Okay, all right. And let's find your work here. want images first? You want?
Yeah, well, they're in order 1 through 5, so we'll do-
Okay,
you
all
might
right.
have to click. them
So
as I go.
this is how you're going to do it. You're just going to double click on these. You're going to drive,
Okay,
and let's see.
so the first one's my telescope.
This one right here.
I believe so. He gave them to you in order, so 1 through 5 is how I'll do my speech.
Am I still inside keynote? Okay. All right. Let's get rid of some of this stuff here. Let's get rid of PowerPoint.
There I am. No.
Let's get rid of. We've been busy on my computer today.
Oh, yeah. Without it,
Mhm.
tough to do.
Oh, it's trying to open in Keynote. I see. Mhm. Let's do it this way.
Yeah, thumbnails is good if I can see it. So there it is, yeah.
Okay. All right. So what we're going to do, I'm going to stop sharing. We are going to go back over here and share the screen and come right over here, share. And now, John, you just click on these
Go ahead, you
images.
can bring the first one. That's it, just double click it.
I'm renaming it for you.
Those are all my images. Yeah.
Here we go. He looks like Superman there.
If I
It's great.
struggle, just click on them. or would I
Yeah,
close that. and
just
click
put
on
the
next
mouse
one?
right over the picture, the
Okay.
thumbnail, and double click, and there you go.
Okay,
Okay.
my name is John Schwartz, not to be confused with May the Schwartz be with you, Spaceballs. But I'm an astronomer and astronomy sketcher. I've been doing it for almost 40 years. And I show a lot of people pictures and they always ask me, you know, I don't really see too much. And I say, well, you've missed the whole thing. They haven't looked. They said, I've already seen it. So what I do is you have to be able to really study the image, and that's going to help you show much more detail when you're viewing, you know, because your eye is trained, so you're able to see a lot more. And that's why sketching is so important. It'll teach you to see a lot more in your astronomy when you're viewing. It's very helpful. So, you know, through history, a lot of the sketchers have done sketching to document data, take pictures of, you know, what they can see based upon their bias. You know, they see pictures based on what their colleagues are doing, and they didn't have the advantage of astronomy like we do. You know, we have photographs and a lot of detail that we can actually use to do better sketches. So let me move to the next image. Probably, I'm having, is that the X to close it, Scott? Oh, yeah, it's excuse
Yeah,
me,
there you go. Red dot.
I'm Android.
Red dot right there.
Okay,
All right. Put it right over the picture, right over the thumbnail. There you go. Double click right there. There you
Okay.
go.
so this is Sir Lord John Herschel. This is a picture of what he does. And in the early days when they sketched, they would have to use micrometers to actually document the star positions. And then they would also use triangles to plot stars and get a very good, accurate pre-sketch and an outline. And then they would also put a grid pattern on that. And over many nights, he would go out after he did the whole layout and the working skeleton. He would add detail, you know, in each little square each night until he could compose a whole image. You know, he thought it would be impossible to sketch an image like this, but he was able to do it because he did it at one sector at a time. And after 7 nights, that image came to life, and then he had it and it was complete. So that's his image of Orion. I inverted it so it looks more natural. And you can see how accurate that actually was for not even using a photograph or having any, modern day stuff like killer eyepieces like we have, Explore Scientific or Teleview, or an instrument like I got. They were just using small speculum type mirrors without even killer eyepieces. They would look down the tube and actually draw those. So they were very gifted people. Their drawings were much different from one person to the next because of their location or the instrument they were using, or even their eyesight was different. So when you looked at an image that they all drew, it didn't look anything alike. It just looked really different. Like each person drew something absolutely different. Okay, so now I'll go again, next image.
Okay.
I've got to get an iPhone someday. So these guys use pretty much the same sketching methods that we would use today. They would use a white paper and a candle with red filter and probably graphite or even carbon pencils. And then they would just smudge it with their fingers. But this is my modern day kit for sketching. So for templates, instead of going through the painstaking ordeal of drawing grids and doing these complicated micrometer readings, I will just use a template of a picture that I had taken or something I had already drew to plot my stars. You could even use a Star Atlas or Stellarium, any one of these programs, to get your stars plotted exact in the general outline, and then you go to work filling it in. So those are basically all my tools. I use the book. Another style of sketching is the Mellish technique, and that's where they use black paper with white charcoal powder. So you just use white chalk and sand it on there and use a brush, and you start working the core or the fuzzy part first, and then working outward, and then you can add more detail with more stark white charcoal pencils, and then stippling with a certain brush, and then you create an almost actual representation of that object, and it looks totally realistic. So I was experimenting with that. Most of the time I like to do pencil because it's easier to see on your board at night with the red light. It's really tough to do this sketching on black paper.
So, we're going to try it this way.
Yeah, you want to just pop them up for me.
Let's just close one. This is good. Yeah.
Okay.
You go over there. And you go.
Now, you don't need a big telescope to do this like I have.
Oh, okay.
You don't need to be an artist. You don't need to be an artist.
Just push one button and it'll go through all your images.
Okay, let's go back to the one out. Keep going. Go to the one more, next one back. That one.
Okay, so now you push that
Okay,
button and it'll advance.
beautiful. Okay, so sorry, this was an actual eyepiece sketch from Mount Inos. Whoa, why does it change? You see that? Okay, well, anyway. Okay, I did, show me.
Stop it.
Oh, got it.
And then boom, 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 boom.
Okay, perfect. Sorry about this, guys. I only work with paper. Okay, so this is NGC 5907. Of course, in my big scope, it looks, what the? You know, I did. Okay, hold on. I hit it once. Okay, now space, hit it. There it goes. Okay, so this is an idea of how they would do their drawings. They would do them, pretty simple like this. Of course, my bias has changed because I have access to a huge telescope, incredible eyepieces, filters, and then also photographic pictures that I can work with. The trick is, if you're going to use photographic elements in your image that you sketch, you have to be able to see that in your view. So with averted vision, that's achievable. And that'll take your image to a higher level. But a lot of people don't believe that that's your image. So. Uh-oh, they didn't like that. This one. Okay, so this was actually probably took me 2 years to do. This was a pencil sketch of the Swan Nebula. So I've done several renditions, and then I had access to my buddy's 32-inch slipstream and my 28 with the killer filters, and the Nikon Nav 17 eyepiece was essential in getting these faint details. So what you see there is basically a pencil sketch blended with stubs and taking erasers to remove material, and then darker soft pencils to bring out the darker. So that's how those guys would portray their picture at first. And then what I would do is invert it. And so this is actually the inverted picture. And that was exactly what it looked like looking through my 28-inch with the NPB filter. I could see all that external stuff, and the inside of the Swan was just amazing. The details and the little structural tendrils and twisting, filaments, just amazing to see that through the 28. And this has probably been, I bring these into Photoshop Express after I invert it, which is a free program you can get on your phone. And then I do levels and contrast and just keep playing with the image. And then to do the actual painting, I'll use Samsung Photo Editor, which is a dedicated program on your cell phone that allows you to take and paint. You can actually paint, much like real Photoshop, but I haven't learned that one yet. So these are all done on my cell phone. And this was an entry I did in the sketch contest in Cloudy Nights. Of course, I didn't win, but I thought it was a winner. But as they say, like William Temple, he did not believe that Sir Lord Ross's picture of M51. He said there are no spirals, because he was looking through an 11-inch telescope. He couldn't see that, because back then even the mirrors were made of speculum or whatever. They weren't like today. So, they disputed his finding that it was a spiral galaxy, and that, he had to prove it by showing him the picture he drew. And then finally, with the later instruments, they had proved that they are spiral galaxies and brother systems to our galaxy. So the last one I have is this is the Eagle Nebula. And this was a composite image. The top stars were like from a cell phone image. The center star was actually a ZWO image taken through my 28-inch. And the optics are amazingly sharp. So I used the 32-inch to try to create this image. But it's a very fast f3.3. So the contrast isn't as good as what I'm getting at f4.3. So I inserted my picture in there and I showed it to him. He swore I used Hubble's picture, but that is actually the photograph through my 28-inch telescope using a ZWO camera, 1600 millimeter pro, and then a for H alpha and a 294C for color. But that's pretty amazing what you can do with this stuff. And I mean, we're just blessed to be able to have access to this equipment and technology to be able to do these things, That's just a few, probably maybe 10, 15-second images combined. And, because we're alt-az, so we're not really tracking equatorially. So we can't really take, like long hours of photos. If we do, we have to just hand pick, and you have field derotation to deal with as well. So I believe that's all of my, oh, this is my one. This was another sketch contest entry. This is actually the live visual view that I was able to obtain with averted vision using a series of filters and eyepieces. I think I used, in Merkos, I was using a 92-degree Explorer Scientific, amazing eyepiece. I was just blown away. And then he had a, one of those new Lumicon Gen 3 03 filters on. Those are a little bit of light obscuring for me with the smaller aperture. I chose the NPB, but this is a combination of actual live views and sketches. And this was done in black and white first, well, white on black and then inverted. And then I refined the image, time and time again. I spent a couple years on this image too, going out and finishing up the details and, the finer details. If you look in even a large telescope, it's really hard to see the pillars of creation. So you really have to know what to look for. And from all the sketching I've done, it's just improved my ability to see the fainter details and the stuff that's overlooked that most people don't really look at because they don't see it because they don't spend enough time on that object. We're not too good. What would you say they are, Bjorn? I think we're what, Bortle 3 or 4? The squib was 21.48, which is a light meter. It's Mount Pinos in California. And we've been really affected by all the growth in Gorman and then Fresno and Bakersfield. So on the nights where the clouds come in, much like here, and all the coastal valleys are buried in cloud cover, then we get the most spectacular nights. But I mean, for this location, it's probably one of the closest places you can get. I would say it's probably Bortle 3, maybe Bortle 4. And it's deteriorating, A lot of the astrophotographers like Tony Hallis and those people, Michael Stecker, and a lot of them moved up north because it's much better up there. And Pinos was degrading rapidly. I mean, it's like one of the last places we have left that's really good. Or if you want to drive to the desert, or, it takes probably an hour and a half to get there from here. So
Yeah, it'd be one of the closer places, that's for sure. Yes, sir.
Yeah, on the light pollution front, since you brought it up, I want to point out that the Los Angeles Astronomical Society strictly conditioned reports of how enforcing its rules. And I think it was last week, we had 3 of the county officials and their families come visit our dark sky sidewalk valley, which is not far from Mount Pinos.
right.
And they were very impressed by us, what we were doing. They saw the light pollution and they've already begun instructing county light pollution county officials to look at housing developments and begin to enforce rules they haven't been enforcing. So we had a positive effect. And if you want to sign a petition, there's a link to it on the LAAS website. You can go there and spread the word. So we have had some effect, positive effect on that. But I did have a question about this, and that's when you do your sketching, do you sketch on paper and digitize it, or do you do your sketching directly on?
No, well, I do both. For some planetary work, I'll do actual live eyepiece sketch on my cell phone. I prefer to do something like these. These start out as a sketch, and I've done many renditions to get to that level. And, quite a few of them got scrapped. But I always try to do on the showpiece objects, I like to do them as a sketch first to keep the integrity there. But it's hard to help myself once I get into that program, like a Photoshop or any of these programs. You can create illumination effects that are just magical, that are very hard to get, by a sketch. And sometimes when you're working, the beauty is when I'm painting with my photo editor, Samsung, you know, like for instance, the little guy on the right, you see how those wispy, the cool gas is just drizzling down off the body of that. So that was done, you know, sketching, and I have to work with opacity and then different brushes that are more like an airbrush as opposed to a hard edge brush. But this particular one was started as an actual visual sketch. You know, I had the basic shapes and shading, but I really was able to take it further based on notes, and then also using some photographic evidence from the pictures I had taken through my scope, but not, you know, painting what I didn't see. This is actually what I could see with averted vision looking through my 28 and the 32. You know, having those apertures really helps, and the amazing filters too, like the NPB, it's amazing filter. And then when you put it on like one of Scott's eyepieces, those wide field killer eyepieces, I mean, it just opens up. So yeah, this is actually sketched. 80% was you know, pencil sketch, black and white. Then it was inverted, and then I did some additional illumination. Now on the front of the head of the main pillar, I had seen those pillars so many times from my photograph that I just kind of knew how to paint the little tendrils coming off the top, you know, the light that's illuminated from those stars. And I was really happy with this one. Unfortunately, I didn't win again, but it's not about winning. It's about, you know, practicing and using your skills. I mean, just like John Herschel did, he used those templates that he created, and they also used a Lucy. Are you familiar with that? But that would be for their daytime drawings. That's like you look in a prism like this and you can see your subject matter here, but on your paper, you see that subject matter. So you can actually draw it. So, you know, I'm not doing it entirely as they did it. I've been affected by all the things that we have, like photographs, Hubble images, and all the amazing stuff that I get to look at. And I incorporate that in my drawing because it's affected me. You know, I want to show as much as I can, like you're actually there. And thank you.
I find myself closing one eye.
Well, we're always up there. Yeah, I'm just so lucky that I was able to get that telescope. You know, the game is you start with a small scope and you work your way up. And honestly, I had a 24 before this, and I sold that to get a 28. That 28 I had to get rid of because I had some financial troubles with the family, and I had to take care of it. So I sold that. And then in 2 years' time, the universe gave me another 28, which was better. Of course, I know opticians too. But I mean, it took a lifetime to get that 28. And within 2 years' time, I was able to get it again. So, you know, the power of manifestation is amazing if you believe in it. Yes, sir.
Well, the bright star between the two main pillars, they're least it's like you drawn some arcs around it. And it's with like diffraction on them.
Yeah, originally I had some diffraction spikes.
Well, no spikes, I mean, areas.
Yeah.
Is that or is that some structure?
Well, it's probably a combination of both. I did notice some diffraction from that bright star. You know, the optics are extremely good, and I had really good collimation. So a lot of these stars, when I'm working them digitally, you know, if I don't do everything in one try, when you save that and come back to it, at least on your cell phone with Photoshop Express, they start to turn into little squares, or they'll change shape. So, or I'll actually delete it by accident and have to start over, which I've done that a few times, and I want to yell out. And I mean, I'm talking 10 hours of work on one picture, and it's like, oh my gosh, this is it. I've done it. And then I realize I deleted it. I'm about to yell, and I just go, John, it's practice. Practice makes perfect. And then I go, yeah, practice. And then I'll start all over. But so yeah, a lot of the stars I have to go back and redo. I am now going to be using a Wacom tablet and with Photoshop, but you know, that's a whole different game. As you can see, I can barely operate this. So I'm going to be in trouble for a little while. But you know, what you can achieve with those is amazing. And it's all the tools we have today. I mean, I think they would use them in the 19th century if they had access to them, you know.
Do you have a website or a page where these things?
I post them on cloudy nights, but I haven't posted in a while. I'm going to be working on an actual site. I may actually do my gallery, start putting them in my gallery at cloudy nights. If you go on the sketching forum or even to my profile, will tell you I'm JM Schwartz, John Matthew, but that's my handle. And I you know, eventually have enough. I'm almost through 110 objects. I've probably got like 50 to go. That's a lot, you know, and if I could get those all together, and then some of my other premier objects, I'm going to do a special site like drawings.com or create my own website with that, but I haven't gotten that far yet. I just started doing the digital stuff and posting. I've even had some pictures that got destroyed, you know, from the past, that I was able to take this picture and it was all partially burned and crumpled up. And I was able to take that and remaster it digitally, dipping into the color of the actual drawing. It was a pencil sketch. And I recreated that thing, and it was masterful how beautiful it actually looked, you know, after what I had learned from the first time I sketched it in college. But, you know, it's an evolving thing, and these works are never really done. You know, the more you see, the bigger instrument. If I could get more data looking through the 60-inch, I could apply that here, but we're not in a dark sky site. But I did do some amazing planetary nebula sketches through the Wilson that I have. I can show you guys later. And I also brought some prints that I brought of the swan and the eagle that I'd like to give you guys each a copy, and you can take it with you.
That's pretty amazing. I think it's almost like creating a different genre. As Cameron here was mentioning, because you squint and look at this, and it's like
Yeah, I mean, like I said, it's hard. You need a big instrument to resolve those pillars and those filters. The NPB filter and that Gen 303 are some of the best filters to do it with. And it's amazing when you can actually see the pillar like a photo. But again, it's not easy. You have to know what you're looking for. And the sketching has just made me from a casual observer to a very detail-orientated observer. And I see a lot more when I'm at the eyepiece, and I can spend a lot more time, you know, appreciating the image. Now, I also use a cloak sometimes. It's a duvetine, which is a light blocking material from the studio, but you could use a black sweatshirt or a hoodie. You just protect your peripheral, and you keep your head inside of that little dark area, and then it starts to open up. I mean, it's amazing after like 20 minutes under that thing, how much more you can see. So it's a real passion in sharing these with people on the forums and just people that don't have a big instrument and can't always see this. You know, I just want to help people see more out of their own scope if possible. I do recommend aperture, but you don't need it, you know. You could see the pillars in probably a 15, 16 inch on a good transparent night in a dark, dark sky site. Like we were in New Mexico looking through my buddy's 32, and I saw M108, and I couldn't believe the detail. It looked like I was looking at the cloud tops in Malibu Beach from Stunt Road. And then 80, the cigar 82, that was the most amazing thing I'd ever saw, because I could actually see coming out of the core, it looked like coral. They weren't red hydrogen, they were gray, but they had that little illumination on the side of them, so you could actually see the plasma. And that's from Bortle 1, dark sky, you know. So if I can get to Bortle 1, I'm going home. Got to convince the wife. Thanks, guys.
And for those of you watching, I'm sorry that we didn't grab the images correctly to broadcast those, but we're going to go to a video next here. And it's going to look a lot different when I do it. It'll look a lot different when I get to Zoom.
Oh, because you're going to put it in through Zoom or something.
Through Zoom.
Gotcha.
Yeah.
Yeah,
So what we're going to do,
I don't know Zoom. So.
yeah, this is all being broadcasted through about 3 different
Right.
software stacks. So there we go. So the first one is Ecamm Live. This one is Zoom. They're all tied together. Okay. What we're going to do is we are going to go share, and then you have to correctly pick the program, and you have to share the sound. Optimize for the video clip. Share. We are now sharing.
Asking for passwords.
No, it's going to need to do the audio device. So let's see.
There we go. It's in the Zoom frame, right? So that means
Through the Zoom frame. So let's see if you can only try it and see if it works. So here we go. Do you want to talk a little bit about it?
Yeah, I can. Yes.
Go ahead.
And then can we make it full screen too, or?
Yes, we can. Yeah.
So clicking on the green thing will make it full screen. But it's still
Yes. Yes, it will.
Zoom,
Yeah, but go ahead and start talking. I'll take it.
Okay. Hello, my name is Bjorn, and I'm a documentary filmmaker. And I am going to show you a short clip of my new film that I'm working on. It's not finished yet. It's called Sky People. And it's about Mount Pinos and the astronomers that have been going up to Mount Pinos for over 10,000 years, which are the Native Americans, the Chumash. And it's very interesting. I've been going up to Mount Pinos for a little over 20 years now. It's very interesting to see that the majority of the astronomers that are up there that have been going just as long as me or even longer, nobody knows about the Chumash, and everybody is unaware of the fact that Mount Pinos is actually a sacred mountain to the Chumash for numerous reasons that are covered in the film. So again, the film isn't finished yet. Here's a 7-minute version of a trailer, which is also not finished, but I threw it together so I could show you something today. And it's basically about astronomy and our Native Americans in Mount Pinos.
Okay, thank you. Here we go.
places left as far as sacred places, and we could go into our ceremony the way we used to for thousands of years.
Now I feel like I'm just about going into orbit with Saturn with my first spaceship, closer and closer to it. It just brings airs of light and everything.
It is almost a spiritual moment. You see those rings and you ask, are those real?
Just pause and you try to take it in.
Once you see that, you want more.
In Shumash, we believe that there's three levels to the world. There's the upper world where the sky people live, the middle world where we are at, and then an underworld.
In the magazines at the time, there were the same people in every month with their pictures, and all of them shot from anonymous.
I feel the yearning pulling on my soul to get to the top of the mountain each time.
When you hit dusk on Saturday night with a big crowd, there was a buzz in that parking lot. That's beautiful, you know.
I don't think you have to be an indigenous person to feel that energy.
If you close your eyes, you can almost visualize the ancestors standing there.
Native culture really revolves around respect. The Native Americans did not own land, they were on the land. They belonged to the land and not the other way around.
We didn't have a system where if I give you this, I need more than what I give you.
What happens if we're stuck in traffic and it's 110, you gotta be really slow and oftentimes turn your air conditioner off or you're gonna overheat. And they know this, they predict this by showing you on the side of the hill here, there's a big water tank.
One of the things we do as human beings is try to make ourselves comfortable by denying risks that may be around us. There's fires every year that start along the side of the road and can burn hundreds of acres in a matter of a few minutes.
This earth is gonna shake us off for this world, and all we don't try to change what we can do here. She will retaliate, she will go on without us.
Something will die for you today, sacrificing itself for you.
In 2006, we had one of the largest wildfires in California, the Day Fire. That was one of the most powerful lessons that I ever learned about how powerful and how sacred that mountain is.
4 weeks into the fire had consumed 163,000 acres. It was the 5th largest fire in California history. The first ever operational use of the DC-10 turbojet air tanker. But all of that equipment, all of that firefighting force was not sufficient to stop it. We had to develop a dozer line through the middle of the Shumash wilderness and through a mountain that's sacred to Native Americans. The hardest decision that I ever had to face during my career as a district ranger. And as we developed our plans, we gathered representatives from the local tribes. And after that meeting, Adelina Padilla asked us all to gather in a circle. And Adelina said prayers to the Creator and sang songs in her native language.
They were not song. Adelina took over, she was the leader, so we followed her lead.
And as those prayers ended, I looked up and I saw that the weather had changed.
we knew right then and there, I said to myself, everything's gonna be okay. You just, why we knew, I knew that, or why maybe they felt the same thing, we never talked about it, it was just something you knew. And it was. So it was like a miracle.
The winds just changed like that. They came out of the north, and the cold winds out of the north, and the warm winds out of the south. It started to rain. And that was the end of the day fire. I get chills about this because I have no explanation for it. I can't explain what happened that day. I can only say that it did happen that day.
We were all very thankful and amazed when that happened, regardless of the explanation for it. It was a very powerful day.
As the Native Americans say, everybody approached that in a good way. In a good way, with an open heart, with compassion, with humility, with respect, with hope. And it's what happens when people come together in a good way. I keep going back to that phrase, in a good way. There's definitely a lot of positive energy that was all directed that way, and the circle probably focused some of that energy.
Okay, everyone. Well, that's going to be a rerun, right? Here we go.
So you guys all saw John as